We perceive our world as a continuous, unbroken whole. Time seems to flow forward without interruption. Space appears as a perfect canvas, something you can, in principle, divide forever. When you move, you pass through every point between your start and your end. This experience is so fundamental to us that we rarely, if ever, question it. It's the silent assumption that shapes our reality. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if this perception, as fundamental as it seems, is an illusion? What if, at the most basic level of existence, that smooth canvas gives way to something else entirely, a pixelated reality where our ideas of continuity no longer apply? This isn't a thought experiment. It's a quiet but profound disagreement at the heart of modern physics. Our two best descriptions of the universe, one for the very large and one for the very small, present two different, and incompatible, pictures of reality. One is smooth, the other is granular, and in the space between them, our understanding is incomplete. Today, we're on a journey to that point of disagreement. We are going to decode spacetime where it seems to break down, and in doing so, question the very fabric of our world. The problem, the unseen pixels. To understand this incompatibility, we first have to appreciate the illusion of smoothness. Think of your reality at this moment. It feels complete, unbroken. If you pour a glass of water, you see a continuous stream of liquid, not a collection of individual drops hopping from one place to another. The sound of music seems to arrive as a seamless melody, not a series of discrete packets of sound. This is the world of continuity, where between any two moments, there is always another moment. This is the world our senses evolved to navigate. As large beings made of trillions upon trillions of particles, we perceive things on a macroscopic scale. From this vantage point, the universe seems continuous for the same reason a high-resolution photograph looks smooth. From a distance, you see a flawless image. There are no visible gaps, just a gentle gradient of color. But if you were to zoom in, you would eventually find the illusion. The image is not a single entity. It's made of millions of individual squares of solid color, pixels. Up close, the smooth gradient is replaced by a grid of discrete blocks. The smoothness was an emergent property, a result of scale. The question facing physicists, then, is a quiet but profound one. Is spacetime itself like that photograph? Is the smooth fabric of reality that we experience just a grand-scale illusion, one that would dissolve into a grid of fundamental pixels, if we could only see it up close? This represents one of the greatest conflicts in modern science. On one side, we have Einstein's general theory of relativity, our best description of the large-scale universe. It presents gravity as the gentle curvature of a perfectly smooth, continuous fabric of spacetime. For Einstein's mathematics to describe the orbits of planets and the warping of space around black holes, spacetime must be continuous. It must be a perfect, unbroken surface. But on the other side, we have quantum mechanics, our best description of the small-scale universe. And it tells a very different story. It describes a world that is inherently quantized or granular. In the quantum realm, energy isn't a continuous flow, it comes in discrete packets called quanta. Light is made of particles called photons. Matter is made of fundamental particles like electrons and quarks. Everything is built from indivisible units. And if everything else in the quantum world is built from fundamental units, why would space and time be any different? Our theories suggest that if we could zoom in to the smallest possible scale, the smooth surface of Einstein's universe would begin to fray, revealing a coarse, pixelated structure underneath. This is where spacetime breaks down. The historical context, the giants of physics. For most of history, the idea of a pixelated reality would have seemed nonsensical. The world was as it appeared. This intuitive view was first formalized into the language of physics by Sir Isaac Newton. In Newton's universe, space was an absolute, infinite, and unchanging stage upon which events unfolded. Time was a separate thing, a universal clock that ticked at the same rate for everything, everywhere. This was an orderly, predictable universe governed by unbreakable laws. Here, space and time were the background, not active participants. And that background was, without question, perfectly smooth and continuous. You could, in theory, divide any distance or any duration in half, and in half again, forever, without ever hitting a fundamental limit. This Newtonian picture of reality was our guide for over 200 years. It was powerful, and it worked. It allowed for the prediction of planetary motion and the tides of oceans. But near the turn of the 20th century, a new understanding began to emerge from the work of a patent clerk in Bern, Switzerland. His name was Albert Einstein, and his work would reshape our conception of space and time. He realized that space and time were not separate, absolute entities. They were woven together into a single, four-dimensional fabric, spacetime. This was the core of his theory of special relativity. He showed that the speed of light in a vacuum is a universal constant for all observers. The consequence of this is strange and profound. Space and time themselves must be relative. They must stretch and shrink depending on one's motion. For a person traveling near the speed of light, time itself would slow down and distances would contract, relative to someone standing still. Newton's universal clock was an illusion. A decade later, Einstein expanded on this with his general theory of relativity. He proposed something even more radical. This spacetime fabric wasn't just a passive stage, but an active participant. Mass and energy, he argued, tell spacetime how to curve. And that curvature, in turn, tells mass and energy how to move. This is gravity. Gravity is not a mysterious force, as Newton suggested, it is the geometry of spacetime. A planet orbiting the Sun is simply following the straightest possible path through the curved spacetime created by the Sun's mass. It's like placing a heavy ball on a stretched rubber sheet. The ball creates a dip. A small marble rolled nearby will follow that curve. That is gravity. Einstein's theory was a monumental achievement. And at its heart was the assumption of a smooth, continuous spacetime. It was a geometric object, and you could zoom in forever and it would always remain smooth. For the elegant mathematics of general relativity to work, continuity was essential. It painted a picture of a graceful, flowing, analog universe. But at the same time, another revolution was taking place, one that would describe a world that was anything but smooth. The quantum revelation, where it all breaks down. While Einstein was reimagining the cosmos, other physicists were looking into the heart of the atom and finding a world that was quietly strange. This was the beginning of quantum mechanics, and it started with what the physicist Max Planck called an act of desperation. Planck was trying to solve a problem with the light emitted by hot objects. Existing theories predicted that a hot object should emit an infinite amount of energy, an absurd outcome known as the ultraviolet catastrophe. In 1900, Planck made a radical suggestion. What if energy was not released continuously, but in discrete packets, or quanta? This was like saying that money doesn't come in any amount, but only in multiples of a single cent. This idea, that energy comes in fundamental units, was the birth of quantum theory. It solved the black body problem, but it also opened the door to a new, strange reality. The smooth, continuous world of classical physics now had a challenger. The quantum world was granular and digital. Over the next few decades, this picture became clearer. Matter was found to be made of fundamental particles. Electrons in an atom could only exist in specific, discrete energy levels, like being on specific rungs of a ladder, unable to stand in between. The quantum revolution revealed that at its most fundamental level, nature was built from discrete blocks. This raises the question: if energy is quantized, and matter is quantized, what about the spacetime they exist in? This is where general relativity and quantum mechanics come into direct conflict. As we imagine probing smaller and smaller distances, the smooth spacetime of Einstein is expected to break down. The conflict becomes unavoidable at a scale so small it's difficult to describe: the Planck scale. The Planck length is approximately 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros and a 1. To give you a sense of this scale, if you were to expand a single atom to the size of the known universe, the Planck length would be roughly the height of a tree. It may represent the shortest possible meaningful distance. The Planck time is the time it takes light to travel that distance, about 10 to the power of minus 43 seconds, perhaps the shortest possible tick of a clock. At this scale, physicists believe the universe becomes something entirely different. The Heisenberg uncertainty principle suggests that spacetime itself becomes a chaotic, shifting medium. The physicist John Wheeler called this concept quantum foam. He theorized that at the Planck scale, spacetime is not placid, but a bubbling surface where particles of matter and antimatter flash into and out of existence, warping spacetime into a probabilistic foam. In this realm, the smooth geometry of Einstein is gone. Cause and effect become uncertain. The very ideas of before and after, or here and there, start to lose their meaning. This is where our two best descriptions of nature offer two incompatible pictures of reality. General relativity requires a smooth continuum. Quantum mechanics predicts a chaotic, granular one. To have a single, complete theory of the universe, we need a new theory, a theory of quantum gravity. The quest for a new reality, the contending theories. How do we reconcile the smooth world of Einstein with the granular world of quantum mechanics? How do we describe the pixels of spacetime? For decades, some of the brightest minds in physics have been trying to answer this question. From that effort, two leading, but very different, ideas have emerged: loop quantum gravity and string theory. Let's start with loop quantum gravity, or LQG. This theory takes a direct approach. It attempts to quantize spacetime itself by applying the rules of quantum mechanics to general relativity. Its central idea is that the fabric of spacetime is not a continuous sheet, but is woven from a network of finite, interlocking loops. Think of a piece of fabric. From a distance, it appears as a smooth surface. But up close, you see it is made of individual threads. LQG proposes that spacetime is like this. Space is made of discrete atoms of space, fundamental volumes at the Planck scale. You cannot have a volume smaller than this. These atoms of space are nodes in a mathematical structure called a spin network. The links between them represent the quantized areas that border these volumes. Time, in this picture, is not a smooth flow either. It is the result of the constant rearrangement of these networks. It's like a film, which creates the illusion of motion from a series of discrete frames. In LQG, the evolution of the universe is a sequence of these transformations, rearranging the geometry of space. The combination of the spin network and its evolution creates a structure called a spin foam. One appeal of loop quantum gravity is its directness. It predicts that spacetime is fundamentally discrete. It doesn't require extra dimensions or new particles. It takes the two theories we have and melds them, producing a pixelated reality as a natural outcome. It offers a picture of what might happen at the center of a black hole or at the moment of the Big Bang, suggesting that the singularity, the point of infinite density, is avoided, because you can't squeeze anything into a space smaller than a Planck volume. But LQG has its own challenges. One of the biggest is showing how the smooth spacetime we observe emerges from this granular foundation at large scales. The other main contender is string theory. It starts from a completely different place. It's a theory of everything. Its premise is that if you could look at the most basic constituents of the universe, electrons, photons, quarks, you wouldn't see points. You would find that they are all tiny, one-dimensional, vibrating loops of energy called strings. The central idea is elegant. Just as the different vibrations of a violin string produce different musical notes, the different vibrational modes of these fundamental strings produce all the different particles. One vibration pattern appears to us as an electron. Another, a photon. In this view, the entire zoo of particles is just a symphony of vibrations from a single kind of object. This approach aims to unite all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, into a single framework. Gravity, in this picture, arises from the vibration of a specific type of string, a particle called the graviton. However, for the mathematics of string theory to work, it requires some mind-bending components. Most famously, it predicts that the universe has more than the 3 spatial dimensions and one time dimension we experience, perhaps 10 or 11 dimensions in total. The extra dimensions, the theory suggests, are curled up so tightly that they are invisible to us. Another key ingredient is a concept called supersymmetry, which proposes that every known particle has a heavier, undiscovered, superpartner. Unlike LQG, string theory generally treats spacetime as a continuous background on which the strings vibrate. However, many physicists believe that a deeper version of the theory, sometimes called M-theory, will ultimately reveal that spacetime itself is an emergent phenomenon. The problem is, no one is yet sure what that deeper theory looks like. String theory has also faced criticism for its lack of testable predictions. The energies required to see these strings or extra dimensions are far beyond the reach of any particle accelerator we can currently build. The predicted supersymmetric particles have not appeared in experiments. And so, the two quests continue on parallel paths. One attempts to build reality from discrete atoms of spacetime. The other seeks a unified symphony of strings from which spacetime emerges. The profound implications, what it means for us. So, what if one of these theories is right? What if our smooth reality is just a high-resolution illusion? The consequences would extend through our entire understanding of existence. First, for physics, a pixelated spacetime would mean there is a fundamental resolution limit to the universe. There would be a smallest possible distance, the Planck length, and a shortest possible duration, the Planck time. This would resolve the problem of infinities in physics. When our current theories try to calculate values at an infinitesimal point, like the center of a black hole, the equations break down. A quantized spacetime removes this issue. A singularity could no longer be infinitely dense, because it would be impossible to cram infinite matter into a finite number of Planck-sized volumes. The Big Bang might not have been a beginning from a single point, but perhaps a big bounce, a transition from a previous, collapsing universe. The philosophical implications, however, are even larger. If spacetime is discrete, it feels more like a computation. The universe would seem less like a physical object and more like a form of information. Each pixel of spacetime could be described by a finite amount of information, like a bit in a computer. This has led some to explore the holographic principle, the idea that our three-dimensional reality might be a projection of information encoded on a distant two-dimensional surface. It also gives a strange, scientific angle to the simulation hypothesis, the idea that our reality could be a computer simulation. If the universe is fundamentally computational, evolving in discrete time steps, it bears a curious resemblance to how we build virtual worlds. This challenges our definition of what is real. We tend to think of emergent properties as less real than their components. The wetness of water, for instance, is an emergent property of H2O molecules interacting in vast numbers. If spacetime itself is an emergent property, a statistical effect of countless quantum pixels, then the most fundamental container of our reality might not be fundamental at all. What does this mean for our own experience? The smooth, continuous flow of time is deeply connected to our perception of a continuous stream of consciousness. If time itself proceeds in discrete steps, what does that say about our minds? Does our consciousness also tick forward, creating only the illusion of a smooth flow? It forces us to consider that the now may not be an infinitely thin line, but a finite frame in a cosmic film. Our perception of seamless experience would just be a result of our brains being unable to process information at the universe's incredible frame rate. We would be, in a sense, watching a film that we mistake for reality. We began this journey by looking at our own perception of the world, the smooth, continuous flow of reality. We saw how this perception is the foundation of Einstein's theory of gravity, which paints the universe as a graceful dance on a seamless fabric. But we then entered the quantum world, a world built not on continuity, but on discrete, indivisible units. And we found that at the smallest imaginable scales, these two descriptions of reality are incompatible. This forces us to consider a new picture of reality. We've explored the leading attempts to paint it. Loop quantum gravity imagines a universe woven from a network of finite loops, where space and time are fundamentally granular. String theory envisions a grander symphony, where all of reality emerges from the vibrations of infinitesimal strings. Both theories, in their own ways, suggest that the smooth world we perceive is not the fundamental truth. Reality, at its deepest level, is likely digital. But is there a way to know? Scientists are devising clever experiments to look for subtle traces of a pixelated spacetime. By observing light from gamma-ray bursts that has traveled across billions of light years, they look for tiny amounts of dispersion. If spacetime were not perfectly smooth, photons of different energies might travel at infinitesimally different speeds, an effect that could become noticeable over cosmic distances. So far, these observations have come up empty, suggesting spacetime is remarkably smooth. Other experiments are being designed to search for a predicted, holographic noise, a fundamental fuzziness that could be the signature of spacetime pixels. We have the theoretical frameworks and the first experimental tools to ask the question: what is the ultimate nature of reality? Is it the continuous river our senses tell us it is? Or is it more like a ticking clock, a cosmic computer processing information on a grid of unimaginable fineness? We don't have the answer yet. We are explorers on the coast of an unknown continent. But the journey has shown us that the universe is far stranger and more mysterious than we might have imagined. So, a final question. Having looked over the edge of this idea, what do you think reality is truly made of? An unbroken canvas, or an endless collection of dots? If this journey into the nature of reality has sparked your curiosity, and you want to continue exploring these questions, consider subscribing. The mysteries of the universe are vast, and we are only just beginning to decode them. Why Newton and Einstein were both wrong about spacetime. For a long time, physics gave us a clean, predictable map of the universe. It was a story of cause and effect, of planets moving in reliable paths, and of time moving forward at a steady, shared pace. First came the world built by Isaac Newton, a reassuringly orderly universe set against a fixed and absolute backdrop of space and time. Then, Albert Einstein quietly offered a new perspective, revealing that space and time were not a static stage, but a single, connected fabric, spacetime, that could bend, warp, and even ripple. This new map was even more remarkable. It suggested the existence of black holes and gravitational waves long before we had the tools to find them. And it has passed every test we've put it through, from a small wobble in Mercury's orbit to the faint echo of colliding black holes a billion light-years away. But this map, as beautiful and as useful as it is incomplete. At the smallest, most fundamental scales of reality, the elegant ideas of both Newton and Einstein seem to unravel. When we follow their equations into the extreme environments of a black hole's center or the universe's first moments, they stop making sense, returning answers that feel like nonsense. Infinity. This is not a small error. It points to a quiet, deep problem in the fabric of reality itself. A place where our two most successful descriptions of the universe, general relativity and quantum mechanics, do not agree. The story of spacetime is the story of a long effort to draw a true map of the cosmos. And what we have discovered is that the map we use is hiding a place where our understanding goes blank. Newton's universe, the quietly ordered stage. To understand where physics became uncertain, we first have to appreciate how right it was for so long. For more than 200 years, the universe seemed to run on Newtonian mechanics. And it was a calm, orderly place. Before Isaac Newton, the world was filled with mystery. The heavens and the earth were thought to follow different rules. But Newton, with his Principia Mathematica published in 1687, suggested they were one and the same. The same force that caused an apple to fall from a tree was the force that held the moon in its orbit. Gravity was universal. His laws of motion were so precise they could describe the future. If you knew where an object was and how it was moving, you could calculate its entire path. It was a predictable, clockwork universe, wound up and left to run according to unchanging laws. For this clockwork to function, it needed a place to exist. Newton offered this with his ideas of absolute space and absolute time. He described time as something that, from its own nature, flows equably without regard to anything external. And space as something that remains always similar and immovable. What does this mean? It means that, for Newton, time was like a universal river, flowing at the same rate for everyone, everywhere. A second on Earth was a second on Jupiter. It was the master clock of the cosmos. Space was the infinite, unmoving stage where the events of the universe played out. It was a fixed, invisible grid against which all motion could be measured. An object was either truly at rest or moving at a true speed through this grid. This might sound like a philosophical idea, but Newton believed he had found a way to observe it. He imagined a simple experiment, a rotating bucket of water. At first, the bucket and water are still, and the water's surface is flat. Then, you spin the bucket. Initially, the bucket turns but the water inside does not, and its surface stays flat. There is relative motion between the bucket and the water, but the water's shape is unchanged. Then, friction begins to act. The water starts to spin with the bucket. And as it does, something interesting happens. The surface of the water becomes concave, curving upward at the edges. Soon, the water and the bucket are spinning at the same speed. There is now no relative motion between them, yet the water's surface is curved. Finally, if you stop the bucket, the water keeps spinning for a while, its surface still concave, until it eventually comes to rest and becomes flat again. Newton asked a simple question. What is the water spinning relative to? It cannot be the bucket. When there was relative motion, the surface was flat. When there was no relative motion, the surface was curved. The curvature, Newton reasoned, must be the result of a true, or absolute, motion. The water was not spinning relative to the bucket, it was spinning relative to absolute space itself. The invisible stage of the universe was making its presence known in the shape of the water. For Newton, this seemed to be quiet evidence that absolute space was real. This framework was incredibly successful. It allowed astronomers to predict the return of comets, to discover new planets from small disturbances in the orbits of known ones, and it helped lay the foundation for the Industrial Revolution. Newton's map of reality was clean, elegant, and it worked. The universe was a grand, predictable machine. For 2 centuries, there was little reason to doubt it. But small, quiet problems were beginning to appear. Einstein's correction, a new kind of fabric. By the end of the 19th century, Newton's clockwork universe was the foundation of science. But a few quiet problems remained. One was the orbit of Mercury. Newton's law of gravitation made very precise predictions about how planets should move. It was right for every planet except one. Mercury's orbit wobbled. The closest point of its orbit was slowly advancing by a tiny amount each century that Newton's theory could not explain. It was a very small discrepancy, just 43 arcseconds per century. But in an orderly universe, even the smallest inconsistency suggests something about the mechanism is not fully understood. At the same time, the study of light and electromagnetism was creating a different kind of puzzle. The work of James Clerk Maxwell had shown that light was a wave that traveled at a constant speed, c. But a constant speed relative to what? In Newton's universe, the speed you measure should depend on how you are moving. If you were in a car and turned on the headlights, you would expect to measure the light moving away from you at c. But someone on the sidewalk would measure it as c plus the speed of your car. But famous experiments, like the one by Michelson and Morley, showed this was not true. No matter how an observer was moving, the speed of light was always the same. This was a direct contradiction of Newtonian ideas. It challenged the very idea of absolute space and time. This is where a young patent clerk named Albert Einstein entered the story. In 1905, he published his theory of special relativity, which was built on two simple but profound ideas. The laws of physics are the same for everyone in uniform motion, and the speed of light is the same for everyone. The consequences of these ideas were strange and unfamiliar. If the speed of light is constant, something else must be flexible. That something was Newton's absolute space and time. Einstein showed that space and time are not separate. They are relative. How you experience time and distance depends on your motion. For someone moving very fast, time itself would appear to slow down, and lengths would seem to contract. There is no universal river of time. Each person carries their own clock. There is no fixed stage of space. Each person has their own ruler. Newton's separate concepts were merged into a single, unified thing, spacetime. This was a major shift in thinking, but it was just the beginning. For 10 years, Einstein considered the nature of acceleration and gravity. This led to what he called his happiest thought. He imagined a person in a falling elevator. As they fall, they feel weightless. If they were to drop objects from their pockets, the objects would float beside them. In their immediate surroundings, gravity would seem to have vanished. This insight was the key. Einstein realized that gravity was not a force pulling objects toward each other. Gravity is acceleration. The feeling of gravity is equivalent to being in an accelerating frame of reference. This is the principle of equivalence, the foundation of his new understanding of gravity. In 1915, Einstein presented his theory of general relativity. It was a complete reimagining of gravity. In Newton's universe, planets orbit the Sun because of a gravitational force. In Einstein's universe, there is no force. Instead, massive objects like the Sun warp or curve the fabric of spacetime around them. Planets are not being pulled. They are simply following the straightest available path through this curved spacetime. As the physicist John Archibald Wheeler summarized it, spacetime tells matter how to move. Matter tells spacetime how to curve. Suddenly, Newton's stage was not just gone. It had become an active participant in the cosmos. Spacetime was not a passive background. It was a physical thing that could be bent, stretched, and made to ripple. This new map made remarkable predictions. It explained Mercury's quiet wobble perfectly. It predicted that light from distant stars should bend as it passes the Sun, a phenomenon confirmed during a solar eclipse in 1919. It predicted that time itself should run slower in stronger gravitational fields, an effect that is now a necessary correction for our GPS systems to work. Most strangely, it predicted objects so dense they would curve spacetime infinitely, creating a region from which nothing could escape, black holes. And it predicted that the movement of massive objects could send ripples through spacetime, gravitational waves. For a century, these were just ideas. But in September 2015, the LIGO experiment detected gravitational waves from two merging black holes, and the discovery was announced in February 2016. We had heard the sound of spacetime itself. Einstein was right, in a way that was difficult to imagine. General relativity is one of the most beautiful and successful theories in science. It is our best map of the cosmos on the largest scales. But there is another map, a map of the world at the smallest scales. And the two maps do not seem to fit together. The quiet flaw, where the map is blank. The 20th century gave us two great descriptions of reality. General relativity is the theory of the very big, stars, galaxies, the universe. Quantum mechanics is the theory of the very small, atoms, electrons, and the particles that make up our world. Both have been tested with incredible care and have been proven right again and again. General relativity describes the cosmos with elegant, deterministic equations. Quantum mechanics describes the atomic world with its own rules of probability and uncertainty. For most situations, this is not a problem. The effects of gravity on a single atom are so small they can be ignored. The quantum strangeness of a planet is so negligible it can also be ignored. The two theories work in their own separate domains. But there are two places in the universe where these domains meet. Two places where the very big is also the very small. Those places are the center of a black hole and the beginning of the universe. And in those places, our two greatest theories do not agree. Consider a black hole. According to general relativity, when a very large star collapses, it compresses its mass into a point of zero volume and infinite density. This is a gravitational singularity. At the singularity, the curvature of spacetime becomes infinite. It is a point where the known laws of physics seem to break down. When you put the numbers for a singularity into the equations of general relativity, they return infinity. This is not a physical answer. It is the theory telling us that it has reached a place it cannot describe. Now consider the other description, quantum mechanics. The quantum world is not like the orderly clockwork of Newton or the smooth curves of Einstein. It is a world of quiet, constant, probabilistic motion. One of its key ideas is Heisenberg's uncertainty principle. This states that you cannot know certain pairs of properties of a particle with perfect accuracy at the same time. This uncertainty is a fundamental property of reality. It allows for tiny amounts of energy to briefly appear from nothing, as long as they disappear again quickly enough. This energy often takes the form of virtual particles, which appear and then vanish a moment later. This means that even a perfect vacuum is not truly empty. It is filled with a constant, subtle tremor of these fleeting particles, a state physicists sometimes call quantum foam. This quantum foam is everywhere, but it is usually unnoticeable. However, if you could zoom in to incredibly small scales, far smaller than an atom, the energy of these fluctuations becomes immense. Now, let's bring Einstein's idea back. General relativity tells us that energy curves spacetime. So what happens when you have the enormous energy fluctuations of the quantum foam at incredibly small distances? According to the combined logic of the two theories, spacetime itself should become a chaotic, fluctuating environment. At the smallest fundamental level, known as the Planck length, an almost unimaginably small 10 to the power of minus 35 meters, the geometry of spacetime should no longer be smooth. The gently curving fabric that Einstein described would, at this scale, be torn apart into something unpredictable and chaotic. Here lies the quiet contradiction. General relativity is built on the idea that spacetime is smooth and continuous. Quantum mechanics suggests that at the smallest scales, it must be something else entirely, something chunky and uncertain. The two descriptions are incompatible. This is a mathematical problem. When physicists try to write a single theory that includes both general relativity and quantum mechanics to describe the center of a black hole or the first moment of the Big Bang, the equations stop working. They produce infinities, which tells us that our description of the world is incomplete. We have a nearly perfect map for the large-scale universe and a nearly perfect map for the small-scale universe. But at the most extreme and important points, where gravity and the quantum world must meet, the maps contradict each other. Newton's absolute stage was replaced by Einstein's dynamic fabric. But now it seems that this fabric itself dissolves into something we do not understand at its most fundamental level. Both maps are correct in their own way, but they are also incomplete. They are approximations of a deeper, unknown truth. And the patient search for that truth, for a single, unified map, is the greatest challenge in all of modern physics. The search, mending the map. So, our understanding of physics seems to have a quiet flaw. Our two great descriptions of the universe, general relativity and quantum mechanics, cannot be reconciled. This is not just an inconvenience, it is a sign that we need a new idea. A deeper understanding of reality that can unite the world of the very large with the world of the very small. This search is for a theory of quantum gravity, and finding it has been a long and patient effort for many of the brightest minds on the planet. They have come up with some truly unfamiliar ideas. There are two main approaches, each taking a very different path to mending the map of reality. The first, and perhaps most famous, is string theory. This theory makes a strange and elegant suggestion. The fundamental parts of the universe are not tiny points, like electrons. Instead, at the deepest level, everything is made of tiny, one-dimensional vibrating strings of energy. According to this idea, every particle we see is just a different note played on one of these strings. The way a string vibrates determines its properties, its mass, its charge. The rich variety of particles in the universe could be just the result of a symphony of these tiny strings. How does this help with gravity? String theory predicts that one particular vibration of a looped string would have the exact properties of the graviton, the hypothetical quantum particle that carries the gravitational force. In this way, string theory naturally includes a quantum description of gravity. It avoids the infinities by smearing interactions over the tiny length of the string, instead of at an infinitely small point. However, string theory comes with its own unusual features. For its mathematics to work, it seems to require a universe with more dimensions than the 3 of space and 1 of time that we experience. In most versions, 10 or 11 spacetime dimensions. The idea is that these extra dimensions are curled up into a tiny, complex shape at every point in our space, so small that we do not perceive them. Despite decades of work, string theory has so far struggled to produce a unique, testable prediction, leaving it, for now, in a realm of mathematical beauty. The other leading approach is called loop quantum gravity, or LQG. Instead of starting with particles, it starts with Einstein's spacetime and tries to quantize it. It takes a more direct approach. If the problem is a conflict between a smooth spacetime and a chunky quantum world, LQG suggests, let's make spacetime itself chunky. Loop quantum gravity proposes that the fabric of spacetime is not a continuous sheet. Instead, it is a network, a fabric woven from a finite number of discrete, indivisible loops. These loops are the fundamental atoms of space itself. You cannot have a distance smaller than one of these loops. You cannot have a smaller area or volume. Space itself comes in indivisible pieces. In this picture, space-time is a granular network. The evolution of this network over time is called a spin foam. This fundamentally granular structure avoids the infinities that appear in black hole singularities. According to LQG, the collapse of a star does not end in an infinitely dense point. Instead, it reaches a maximum, finite density and then, because of quantum pressure, bounces. LQG suggests that the Big Bang itself may not have been the beginning, but rather a big bounce from a previous, contracting universe. Unlike string theory, LQG does not require extra dimensions. It is a more conservative attempt to combine the known principles of general relativity and quantum mechanics directly. However, like string theory, it has its own deep mathematical challenges, and showing how our smooth-looking spacetime emerges from this granular network remains a difficult problem. So here we stand, at the edge of our own understanding. We began with Newton's orderly, clockwork universe, with its absolute stage of space and time. It was a beautiful map, but it was incomplete. Einstein gave us an even better map, a dynamic, curving fabric of spacetime. It has been a remarkably successful map, guiding us to black holes and letting us hear the echoes of cosmic events. But we now know that this map, too, is not the full story. When we follow it to the extremes of the cosmos, to the center of a black hole or the first moment of creation, our map becomes blank. The smooth continuity of Einstein's world does not agree with the uncertain, quantized nature of the quantum world. We are left with possibilities, each as unfamiliar as the last. Perhaps, as string theory suggests, reality is a quiet symphony played on tiny strings in a higher dimensional space. Or perhaps, as loop quantum gravity proposes, spacetime itself is not a smooth fabric but a tapestry woven from indivisible quantum loops. Or maybe, the true answer is something else entirely, something we have not yet begun to imagine. What we know is that the simple map of the universe is gone. In its place is a grand and quiet mystery. We are like ancient cartographers looking at a globe where entire continents are still unknown. We know there is a deeper reality, a unified description that can finally mend the quiet flaw in our universe. The search for it is a testament to our relentless curiosity to understand our place in the cosmos. The map is incomplete, and that is perhaps the most interesting thing in all of physics. Why smooth spacetime is the biggest illusion in physics? From the graceful arc of a thrown ball to the steady, uninterrupted passage of time, everything your senses tell you about the universe is that it's smooth and continuous. For over 100 years, our best theory of gravity, Albert Einstein's general relativity, has agreed. It painted this picture of a beautiful, unbroken fabric of spacetime that elegantly guides the dance of stars and galaxies. But that beautiful picture is an illusion, and it's arguably the biggest one in all of physics. Because deep down in the basement of reality, the universe almost certainly isn't smooth at all. When we look at the crushing heart of a black hole or at the smallest scales imaginable, our most trusted equations break down. They start screaming, spitting out infinities, and telling us that our understanding of everything is profoundly wrong. So, what if the fabric of the universe isn't a fabric at all? What if, just like the image on this screen is made of pixels, and everything you see is made of atoms, spacetime itself is made of tiny, indivisible, chunky bits? This is the story of how physics is being forced to abandon one of its most fundamental ideas. It's a journey to the very edge of reality, to explore the wild idea that our smooth, flowing world is built on a quantum, pixelated foundation. The beautiful lie, our smooth, connected world. To get why this is so revolutionary, we first have to appreciate the illusion it shatters. For most of history, we thought about space and time as two totally separate things. Space was just the empty, three-dimensional stage where the drama of the universe played out. It was absolute, unchanging, and you could, in theory, zoom in forever and always find more space. It was a perfect, smooth grid. Time was even simpler. It was a universal clock, ticking away at the exact same rate for everyone, everywhere. A great river flowing from past to future. This was the universe according to Isaac Newton. His laws of motion and gravity, built on this foundation, were stunningly successful. They let us predict the orbits of planets and the fall of an apple with breathtaking precision. For 200 years, Newton's clockwork universe reigned supreme. It worked so well, it really seemed like the final word. But in the early 20th century, a young patent clerk in Bern, Switzerland, named Albert Einstein, started seeing cracks in the facade. He was bothered by a clash between Newton's laws and the new theory of electromagnetism. The equations for light predicted something truly bizarre. The speed of light in a vacuum is constant. It doesn't matter if you're standing still or racing toward a light beam. You'll always measure its speed to be the same, about 300,000 kilometers per second. This completely flew in the face of common sense. If you're on a highway going 100 kilometers per hour and a car passes you doing 120, you see it moving at only 20. But with light, that simple math just doesn't work. Einstein realized that for the speed of light to be constant, something else had to be flexible. That something was the very foundation of Newton's universe: absolute space and time. In 1905, with his theory of special relativity, Einstein showed that space and time are woven into a single, four-dimensional thing: spacetime. The faster you move through space, the slower you move through time. And no, that's not a trick of perception. Time itself actually slows down. Space isn't rigid either, it contracts. The stage of the universe wasn't static, it was a dynamic, flexible player in the game. This was a huge leap, but it was just the beginning. For the next 10 years, Einstein wrestled with an even bigger problem: gravity. Newton's gravity was a mysterious force that acted instantly across any distance. But special relativity had set a cosmic speed limit, the speed of light. Nothing, not even gravity, could travel faster. So how could the Sun instantly keep the Earth in orbit? The answer, unveiled in 1915 with his theory of general relativity, was even more mind-bending. Gravity, Einstein declared, isn't a force at all. It's just the shape of spacetime. Mass and energy tell spacetime how to curve, and that curvature tells mass and energy how to move. Imagine a heavy bowling ball on a stretched rubber sheet. The ball makes a dip. Now, if you roll a marble nearby, it doesn't get pulled by the ball. It just follows the curve in the sheet. That's Einstein's gravity. The Earth isn't being pulled by the Sun. It's following the straightest possible path through the curved spacetime the Sun creates. This theory was the absolute peak of the smooth world philosophy. General relativity treats spacetime as a perfectly continuous and smooth surface. You can zoom in forever, and it will always look smooth and flat, just like the Earth looks flat from where you're standing. No gaps, no pixels, no jagged edges. And this beautiful lie works. It works spectacularly. Its predictions have been proven right again and again. It explained a tiny wobble in Mercury's orbit that had stumped astronomers. It predicted that starlight would bend around the Sun, which was confirmed in 1919. It even predicted gravitational waves, ripples in spacetime itself, which we finally detected a century later in 2015. On the massive scales of our everyday lives, spacetime behaves exactly like this smooth, elegant fabric. It's one of the most successful theories in the history of science. The crack in the foundation. So what happens when we push this beautiful theory to its absolute limit? What happens in the most extreme places in the universe? It's here that the first, catastrophic cracks start to appear in Einstein's smooth picture. The first crack is called a singularity. According to general relativity, if you cram enough stuff into a small enough space, like when a giant star dies, you create a black hole. At the very center of that black hole, the theory says all that mass gets crushed into a point of zero volume and infinite density. A singularity. And at that point, the math of general relativity just completely falls apart. The equations that describe the universe spit out the number infinity. In physics, infinity isn't a number, it's a warning flare. It's the universe screaming at us that our theory is broken. It's a sign that the smooth fabric of spacetime, according to the very theory that defines it, becomes infinitely curved and just stops making sense. Physics itself dissolves. For a while, physicists could tell themselves that these singularities were safely hidden behind event horizons, so we didn't have to look at them. But a second, much deeper crack appeared, one that couldn't be ignored. This crack came from the collision of the two titans of 20th century physics: general relativity, the theory of the very big, and quantum mechanics, the theory of the very small. Quantum mechanics is the rulebook for the tiny world of atoms and particles. And its version of reality is completely different from Einstein's. General relativity is all about smooth curves and predictable paths. Quantum mechanics is about lumpiness, probability, and pure weirdness. Think about matter. A glass of water looks continuous, right? But zoom in, and you find individual H2O molecules. Matter is quantized, it comes in discrete, lumpy bits. Quantum mechanics is the set of laws that governs this grainy world. It says energy comes in packets called quanta. It says particles don't even have a definite location until you measure them. They exist as probability clouds. The quantum world is inherently fuzzy and jittery. For decades, these two theories lived in peace because their domains never really overlapped. General relativity is for big things like planets, where quantum effects don't matter. Quantum mechanics is for tiny things like electrons, where gravity is so weak you can just ignore it. The problem is when you need both at the same time. Situations with immense gravity on incredibly small scales. That happens in exactly two places: the singularity inside a black hole, and the first moments of the Big Bang. And when you try to use the equations of both theories there, they go to war. The conflict happens at a fundamental scale called the Planck length, which is about 1.6 times 10 to the minus 35 meters. That number is so small it's meaningless. If you blew up a single atom to be the size of the known universe, the Planck length would be about the height of a tree. It's the scale where the quantum effects of gravity should take over. And here's the problem. According to quantum mechanics, even empty space is a bubbling, chaotic mess of quantum foam. Particles and antiparticles are constantly popping into and out of existence, borrowing energy from the vacuum. Now, let's bring Einstein back in. He taught us that energy curves spacetime. So all those little bursts of quantum energy should be creating tiny, frantic fluctuations in spacetime itself. On normal scales, this is no big deal. But as you zoom down to the Planck length, the energy of these fluctuations gets insane. The uncertainty principle says the smaller the space, the wilder the energy swings. At the Planck scale, the energy would be so immense that tiny patches of space would warp themselves into microscopic black holes that pop into existence and immediately evaporate. The result is pure chaos. The smooth, gentle fabric of Einstein's spacetime dissolves into a violent, unpredictable quantum foam. The very ideas of distance and location break down. Our two greatest theories of reality give us completely opposite descriptions of what the universe is made of. This isn't a small disagreement, it is the biggest crisis in fundamental physics today. It's a guarantee that our theories are incomplete. There has to be a deeper theory, a theory of quantum gravity, that can bring them together. And right here, at this point of crisis, our story takes a fascinating turn. We've seen the beautiful illusion of a smooth universe start to shatter. Before we dive into the absolutely radical solution physicists are now working on, if you're finding this journey as mind-bending as I do, consider subscribing and ringing that notification bell. We ask huge questions like this every week, and you make it all possible. The atoms of space-time, a radical solution. So how do we fix this? How do you solve the ugly fight between smooth space-time and a lumpy quantum world? How do you get rid of the infinities that break physics? For a growing number of physicists, the answer is as radical as it is elegant. You have to abandon the illusion. You have to admit that the problem is the assumption that spacetime is smooth and continuous in the first place. What if, like matter and energy, spacetime isn't infinitely divisible? What if you zoom in far enough and you hit a fundamental, indivisible, atom of space? This is the core idea behind several leading approaches to quantum gravity. It suggests our universe is basically a high-resolution digital image. From a distance, it looks smooth. But zoom way in, and you find the pixels. You can't go any smaller. The pixel is the fundamental unit. The idea is that spacetime has its own pixels. This idea has been floating around for a while. Physicists like Werner Heisenberg were playing with concepts that hinted at a pixelated reality back in the 1930s, and it was more formally proposed by a physicist named Hartland Snyder in 1947. But at the time, it was a solution looking for a problem. Today, it's at the very heart of the search for a theory of everything. Two of the biggest theories that run with this idea are loop quantum gravity and string theory. They come at it from different directions, but they both conclude that the smooth spacetime we see is an emergent property, not a fundamental one. Let's start with loop quantum gravity, or LQG. It takes Einstein's theory and directly applies the rules of quantum mechanics. In LQG, space isn't an empty container. It's a field, like a magnetic field. And just like that field is made of quantum particles, photons, the gravitational field, which is space, must also be made of quantum bits. According to LQG, space is literally built from tiny, interlocking loops. Imagine a fabric woven from countless little rings. These loops of quantized gravity form a network. Where the loops cross, they create nodes, which are the elementary quanta of volume. You can't have a volume smaller than one of these quanta. The links between them are the elementary quanta of area. There is no space between the loops because the loops are space. String theory takes a different path. It starts by trying to unite all of nature's forces. Its big idea is that everything in the universe, electrons, quarks, photons, isn't a point, but a tiny, one-dimensional vibrating string. The different particles we see are just different notes played on these strings. So where's the pixelated spacetime? It's a bit more subtle, but it's there. The strings themselves have a minimum size, around the Planck length. And since everything is made of strings, it becomes meaningless to talk about any distance smaller than a string. You can't use one string to measure something smaller than itself. This effectively puts a minimum length into the universe, a fundamental resolution limit. The power of these ideas is that they seem to magically solve the problems that broke physics. Let's go back to that black hole singularity. In a universe with a minimum possible size, you can no longer crush matter into an infinitely small point. It's physically impossible. As a star collapses, it would hit a point where the quantum pressure of this discrete spacetime pushes back. Instead of a singularity, LQG predicts you'd get a Planck star, an object of incredibly high, but finite, density. The infinity is gone, tamed by the graininess of space itself. Some models even suggest this Planck star could bounce and re-expand, maybe even into a new universe. And what about that violent clash at the Planck scale? It just vanishes. The whole problem came from trying to apply a smooth theory in a grainy world. If spacetime is fundamentally discrete in quantum from the start, there's no contradiction. The quantum foam isn't a paradox, it's just what spacetime is. Gravity becomes just another quantum force, playing on a pixelated stage. The two warring theories are reconciled because one of them, the smooth picture of general relativity, was just a large-scale approximation all along. The new reality and the hunt for proof. This is a breathtaking solution. But it paints a picture of reality that is deeply weird. If it's true, what does it mean? And more importantly, how could we ever find proof of something happening on a scale so small it makes an atom look like a galaxy? The implications are mind-bending. For one, It could mean that the cosmic speed limit isn't so constant after all. In Einstein's universe, the speed of light is absolute. But in a chunky spacetime, that might not be true. Think of it like walking on a sidewalk. If the sidewalk is perfectly smooth, your speed is steady. Now imagine it's made of uneven cobblestones. If your feet are huge, you'll just glide over the bumps. But what if your feet were tiny, small enough to get caught in every crack? Your overall speed would be just a little bit slower. Something similar might happen to light. High-energy light, like gamma rays, has a very short wavelength. Low-energy light, like radio waves, has a long wavelength. The idea is that if spacetime is grainy, very high-energy light might feel the bumps interacting with the pixels of spacetime. This could cause it to travel ever so slightly slower than lower-energy light. This effect would be minuscule. Over any distance in a lab, it's impossible to measure. But the universe is a very big lab. We can see things like gamma-ray bursts, cosmic explosions that happen billions of light-years away. After traveling for billions of years, even a tiny difference in speed would add up. If spacetime is grainy, we'd expect the high-energy gamma rays from a distant burst to arrive a fraction of a second later than the low-energy ones. Detecting this tiny delay is the mission of observatories like the Fermi Gamma Ray Space Telescope. They stare at the sky, waiting for these explosions, and time the arrival of photons. So far, the results are inconclusive. There have been some tantalizing hints, but nothing solid enough to be a discovery. The hunt is on, though. Finding that delay would be Nobel Prize-winning proof that spacetime is not smooth. Another search is on for the noise of the quantum foam. Incredibly sensitive instruments like LIGO, which detect gravitational waves, could potentially pick up the faint, constant hum of spacetime jittering. New, smaller experiments like G-Quest are being designed specifically to hunt for this signal, trying to turn these wild theories into something we can actually measure. The hunt is getting even more creative, too. Some new theories propose that when black holes merge, they could pinch off tiny remnants called black hole morsels. These would quickly evaporate, releasing a delayed burst of high-energy particles. Finding a signal like that after a gravitational wave detection would be another powerful clue. The search for quantum gravity is finally becoming an observational science. The journey from our smooth, everyday world down to the pixelated basement of reality is one of the greatest intellectual adventures we've ever been on. We started with the comforting illusion of a continuous universe, a picture that led to Einstein's beautiful theory of a smooth spacetime fabric. But we learned that this picture, as useful as it is still an illusion. The infinities in black holes and the ugly divorce from quantum mechanics forced us to imagine something new. That spacetime isn't fundamental. It's an emergent property, rising out of a deeper, discrete, quantum layer. The idea that reality is fundamentally granular, made of atoms of space and time, solves these paradoxes, but it leaves us with a universe far stranger than we ever thought. Is this picture right? We don't know for sure. Theories like loop quantum gravity and string theory are still under construction, and the proof is still just out of reach. We're like people staring at a photograph, convinced that if we could just find a powerful enough microscope, we'd finally see the pixels. The quest to find those pixels, whether it's a tiny delay in starlight from a distant galaxy or the faint hum of quantum foam, is one of the most exciting challenges in all of science. It's a search for the ultimate operating system of the cosmos, and it reminds us that the deepest truths are often the ones that shatter our most cherished illusions, revealing a reality far more wonderful than we could have ever imagined. The universe has a final boss, and it's the Planck scale. We have always been a species that looks. It is a quiet, persistent part of who we are. We have pointed telescopes outward, toward the faint light of the first galaxies. We have aimed microscopes inward, moving through layers of reality from skin, to cell, to molecule, to the atom itself. It has been a long journey of trying to understand the shape of everything. From the largest structures in the cosmos to the smallest particles we know, we have found patterns, and from those patterns we have written rules. We have built equations to describe how the universe moves. And for a long time, it seemed that with enough time, and with large enough machines, no secret could stay hidden forever. But there is a place where this journey seems to end. A fundamental level of the world that seems to actively prevent us from seeing any further. A point where the laws of physics themselves conspire to close the door. A boundary where, if you try to look any closer, the universe creates a black hole, seemingly just to stop you. This is not a story from fiction. It is the story of a forbidden edge to our reality, a place where everything we understand begins to fall apart, the Planck scale. How we learn to see. Before we arrive at that final boundary, we have to understand how we have learned to see the world so far. Our entire picture of the universe is built on our ability to measure it. On our own scale, this is simple. Light from the sun touches a tree, bounces away, and some of it enters your eye. Your brain translates this into an image. We see the tree because particles of light, photons, have carried information from it to us. To see smaller things, we need different tools. The optical microscope uses the same idea. It gathers and magnifies light, showing us the hidden, living worlds in a single drop of water. But this way of seeing has a limit. Light acts like a wave, and you cannot use a wave to see something smaller than its own wavelength. Imagine trying to understand the shape of a tiny pebble by watching how ocean waves move around it. The large, rolling waves would mostly ignore the pebble, washing over it as if it wasn't there. To see the pebble, you would need smaller ripples, waves with a shorter distance between them. This simple idea has guided our entire journey into the small. To see things that visible light is too large to notice, we need waves with shorter wavelengths. We learned to use ultraviolet light and then X-rays. But to see inside the atom, we needed a different kind of wave entirely. This is where one of the strangest and most important ideas in science emerged. That particles, like electrons, can also behave like waves. And the wavelength of a particle is tied to its energy. The more energy you give a particle, the shorter its wavelength becomes. This opened a door to a much smaller world. Our most powerful microscopes, particle accelerators, are not about seeing with light at all. They are machines for creating particles with enormous energy, which gives them incredibly short wavelengths, small enough to interact with the world inside an atom. By sending these high-energy particles toward a target and watching what scatters away, we began to map the inner space of the atom. We found the dense nucleus at its center, and then, by looking even closer with even more energy, we found that the protons and neutrons inside were themselves made of smaller things. Quarks. This became the method. Higher energy meant a shorter wavelength, which meant a clearer picture of smaller things. For decades, this rule has been our guide, leading us deeper into reality. The way forward seemed clear. If you want to see what is inside a quark, you just need to build a bigger accelerator and increase the energy. It felt like a road that would go on forever, limited only by the machines we could build. We believed that with enough power, we could see all the way down to the most fundamental, indivisible parts of the world. We were moving toward a wall we did not know was there. A point where the very rule that guided us, more energy means more detail, not only stops working, but begins to work against us. Two sets of rules. To understand why our journey has a limit, we have to appreciate the two great theories that have guided physics for the last century. They are like two different sets of rules for two different domains of the universe. Within its own domain, each theory works almost perfectly. The first is general relativity. This is Albert Einstein's theory of the very large. It is the rulebook for gravity, planets, stars, and galaxies. General relativity tells us that space and time are not a fixed background. Instead, they are woven together into a single, dynamic fabric called spacetime. This fabric can bend and curve in the presence of mass and energy. What we feel as gravity is just our experience of moving through this curved space. A planet orbiting a star is not being pulled by a force. It is following the straightest possible line through space that has been warped by the star's mass. General relativity describes a smooth, continuous, and predictable reality. It is the undisputed rule for the cosmos. The second is quantum mechanics. This is the theory of the very small. It is the strange, probabilistic set of rules for the world of atoms and particles. In the quantum world, things often do not have definite properties until they are measured. A particle can be in many places at once. There is a fundamental limit to how well you can know both a particle's position and its momentum at the same time. Energy comes in discrete packets, called quanta. Quantum mechanics does not describe smooth paths, but a buzzing reality of probabilities and sudden leaps. It is the undisputed rule for the subatomic world. For most of what we do, these two sets of rules never have to meet. The quantum uncertainty of a planet's position is so small it has no effect on its orbit, so we can use general relativity and ignore the quantum rules. And the gravitational pull between two tiny particles in an atom is so incredibly weak that we can use quantum mechanics and ignore gravity completely. The two theories work perfectly in their separate places. But the universe is a single, unified thing. There must be one underlying story that connects them both, a theory of everything that can describe the dance of galaxies and the uncertainty of an electron. Physicists have been searching for this story for nearly 100 years. And there is one place where the two domains are not separate. A place where their rules are forced to meet, and where they seem to contradict each other. That place is the final frontier of the small, the destination our journey has been taking us to all along. To get there, we have to imagine building the most powerful microscope we can conceive. A machine made to see past quarks, to probe the texture of space itself. We must follow our rule, more energy, smaller scales, to its final conclusion. And it is there, at that extreme, that the two great rules of physics come into conflict. A deeper look. Let's begin a thought experiment. We are trying to see the smallest possible thing. We have already moved past atoms and quarks. We have used the Large Hadron Collider, a 27-kilometer ring of magnets, to accelerate particles to nearly the speed of light. The energies are enormous, and they give us wavelengths small enough to resolve the quarks inside a proton. But for our journey, this is only a step. We want to see if space itself is smooth or grainy. So we imagine a bigger machine. A much bigger one. With every increase in energy, the picture gets a little clearer. But as we continue to increase the energy, to levels never seen before, something quiet begins to happen. A shadow from the other set of rules, the rules of gravity, starts to appear. Remember, Einstein showed us that energy and mass are different aspects of the same thing. This means that a huge concentration of energy is the same as a huge concentration of mass. And as general relativity tells us, mass bends spacetime. At normal energies, this effect is too small to matter. The gravity of the colliding particles is insignificant. But our new machine is different. We are now concentrating energies billions and trillions of times greater than before. We are packing the energy of an asteroid into a space smaller than a proton. And now, general relativity, the rule of the cosmos, begins to notice. The smooth, flat space we were observing begins to warp under the density of the energy we are using to see. It is a strange paradox. The very tool we are using to look, concentrated energy, is starting to distort the thing we are trying to see. Imagine trying to photograph a delicate snowflake, but your camera's flash is so powerful it melts the snowflake at the exact moment the picture is taken. Our situation is even more strange. We are not just melting the object, we are warping the space it sits in. As we increase the energy even more, pushing our ability to see to smaller and smaller lengths, the gravitational distortion becomes severe. Spacetime around our point of observation curves dramatically. Our measurements get skewed. This is the first sign that the rules are changing. The two great theories of physics are no longer in their separate domains. They are now wrestling for control over the same tiny piece of the universe. Quantum mechanics tells us we need higher and higher energies to see smaller and smaller things. But general relativity warns us that this energy has a gravitational consequence. At first, it is a small effect, a slight distortion. But as we get closer to the final, ultimate scale, this consequence becomes unavoidable. We are approaching a point where the laws of physics will build a wall in front of us. The point of no return. We have turned the dial on our ultimate microscope to its absolute maximum. We are focusing an almost unimaginable amount of energy into a single point, trying to create the shortest possible wavelength to get the highest possible resolution. We are trying to look at a region of space so small it is hard to describe. And then, the universe makes its final move. The warping of space-time around our probe reaches a critical point. The escape velocity from that tiny region becomes greater than the speed of light. In that instant, the region collapses under its own energy and forms a microscopic black hole. This is the ultimate paradox. The very act of looking has created something that, by its nature, cannot be seen. We have been stopped, not by a limit in our technology, but by the fundamental rules of the universe working together. We tried to look too closely, and the universe created a blindfold. That energy, our tool for seeing, became the seed of its own undoing. It became so concentrated that it tore a hole in space-time, creating an event horizon, a one-way boundary from which no information can ever return. We cannot get a measurement back. Our experiment has failed in the most complete way possible. And here is the quiet, frustrating part. What if we try to push past this? What if we add even more energy to our probe, to create an even shorter wavelength, to see what is inside that black hole? The result is counterintuitive. According to general relativity, the size of a black hole is proportional to its mass, or its energy. By adding more energy, we do not see a smaller detail. We just make a bigger black hole. The event horizon expands. The blindfold gets larger. Our ability to see gets worse, not better. The universe is not just telling us we cannot look here. It is actively pushing us away. Any attempt to see more clearly only reinforces the barrier, making it larger and more absolute. This is not a technological problem we might solve one day. It is a fundamental limit, woven into the mathematics of reality. It is the point where the quest for smaller collapses. This boundary has a name. It is defined by a specific, incredibly tiny length. A length where the energy needed to see it is exactly the energy needed to turn that region of space into a black hole. This is where the journey inward hits a dead end. This is the Planck length. The smallest possible thing. So what is this ultimate boundary? It did not come from an experiment. No one has ever measured something this small. It came from the mind of Max Planck, one of the founders of quantum theory, around the year 1900. He was not trying to find a limit to reality. He was simply trying to imagine a natural system of units. He wondered if he could take the fundamental constants of the universe, the numbers that seem to be the same everywhere and for all time, and combine them to produce a basic unit of length, time, and mass. He chose three of the most important constants in physics. First, the speed of light, c*, the cosmic speed limit from Einstein's relativity. Second, the gravitational constant, g, which sets the strength of gravity. And third, the reduced Planck constant, h*, the fundamental number of quantum mechanics that determines the scale of its strangeness. These three constants represent our two great theories. C and G are from general relativity, and *h* is from quantum mechanics. Planck found there was only one way to combine these three constants to get a unit of length. When you do the math, you get a number. That number is the Planck length. It is 1.6 by 10 cubed to the power of 5 meters. It is a number so small it is difficult to imagine. It is a decimal point, followed by 34 zeros and then a 16. To give some perspective, if you were to imagine a single atom was as large as the entire known universe, the Planck length would be about the height of a tree. And this is not just a curiosity. This is the scale where the black hole blindfold appears. It is the fundamental resolution limit of the universe. Many physicists believe it is not just that we cannot see anything smaller than the Planck length. They believe there is nothing smaller. The very idea of distance may stop having meaning below this scale. It is like zooming in on a digital picture. At first, you see a smooth image. But as you zoom in closer and closer, you eventually reach the individual pixels. You cannot zoom in any further. The image is not continuous, it is made of discrete parts. The Planck length is thought to be the pixel of reality. And it is not just length. There is also a Planck time. This is the time it takes light to travel one Planck length. It is about 5.4 by 10 to the power of 4 to the power of 4 seconds. This is thought to be the shortest possible tick of a clock, the quantum of time. Just as space may not be infinitely divisible, time may also come in discrete steps. Below the Planck time, the ideas of before and after may dissolve. This is the Planck scale, a realm where the smooth fabric of spacetime unravels into something else entirely. It is a world some have called the quantum foam, a chaotic, bubbling reality where our ideas of space and time break down. Here, our two great theories, general relativity and quantum mechanics, do not just disagree, they fail completely. They produce equations with nonsensical answers, like infinite energies and infinite probabilities. This is the place where our maps end. We have journeyed to the absolute edge of what we know. A place where space, time, and the laws that govern them seem to dissolve into chaos. If you find your mind struggling to picture this pixelated reality, that is a good thing. It means you are beginning to feel the scale of the mystery. This is the frontier. If this kind of calm exploration into the biggest questions in the universe helps you think, consider liking the video and subscribing to the channel. You will not want to miss where the story goes from here. Where the rules break down. The Planck scale is not just a mathematical curiosity. It represents the deepest challenge in modern physics. For a century, we have relied on our two great theories, general relativity and quantum mechanics. But at the Planck scale, both of them seem to fail. General relativity, the theory of the smooth cosmos, predicts a singularity at the center of a black hole, a point of infinite density. Most physicists see infinities not as reality, but as a sign that a theory has been pushed too far and is breaking. Quantum mechanics, when applied to the fabric of space itself, also produces a storm of infinities. The calculations explode. The theories give us answers that do not make sense. This failure is not a defeat. It is a signpost. It is the universe pointing and telling us, the next chapter of physics begins here. The breakdown of our current rules at the Planck scale tells us exactly where we need to look for a deeper, more fundamental story. We need a new map for this place. We need a theory of quantum gravity. A theory of quantum gravity would be the great unifying achievement of modern physics. It would be a single set of rules that describes both the quantum world of particles and the gravitational world of spacetime. It would explain what happens at the center of a black hole and what the universe was like in its very first moment, the Planck epoch, before it was even one Planck time old. In that moment, the entire observable universe was smaller than a single proton. Only a theory of quantum gravity could describe such a state. Finding this theory is the single greatest challenge in physics today. And the reason it is so difficult is the nature of the Planck scale itself. The energy needed to probe this scale directly, the Planck energy, is about 10 to the power of 19 giga-electron volts. Our most powerful machine, the Large Hadron Collider, reaches about 10 to the power of 4. To build a machine that could reach the Planck energy with today's technology, it would need to be the size of our galaxy. We are, for now, locked out from experimenting in this realm. We are like mapmakers trying to draw a continent we can never visit, forced to rely on pure mathematics and faint, indirect clues from the cosmos. It is a staggering challenge. But we are not without ideas. There are several brave attempts to draw a map of this unknown territory. Ideas at the edge. How do you describe a world without space and time as we know them? How do you write the rules for a pixelated, probabilistic reality? This is the challenge taken on by theorists of quantum gravity. Two main ideas have emerged, each painting a radically different picture of what the world might look like at its most fundamental level. The first, and perhaps the most famous, is string theory. String theory begins by changing our most basic assumption about particles. It suggests that the fundamental parts of the universe are not tiny points, but tiny, one-dimensional, vibrating filaments of energy, strains. What we see as different particles are just different vibrational patterns of this one basic object. An electron is a string vibrating in one way. A quark is a string vibrating in another. It is a simple and powerful idea. The entire zoo of particles emerges from the different notes these tiny strings can play. Most importantly, one of these vibrational patterns perfectly matches the properties of the graviton, the hypothetical quantum particle of gravity. For the first time, gravity fits naturally into the quantum world. String theory does not just allow for quantum gravity, it requires it. However, for the math to work, string theory requires the existence of extra dimensions of space, perhaps 6 or 7 more, all curled up into tiny shapes at the Planck scale, too small for us to ever perceive. The second major idea is called loop quantum gravity. It takes a very different approach. It starts with Einstein's theory of general relativity and tries to apply the rules of quantum mechanics directly to space itself. The result is a picture of a pixelated spacetime. According to this idea, space is not a smooth backdrop, but a network of connected, finite loops. These loops of the gravitational field are woven together into spin networks. Each loop contains a minimum possible area, a quantum of area, on the scale of the Planck length squared. These networks also define quanta of volume. Spacetime itself is built from these discrete, indivisible pieces. In this view, space is not in the universe. The network of space is the universe. Time is also quantized, emerging from the sequence of changes as the spin network evolves. This idea is appealing because it comes directly from trying to unite our two great theories without needing extra dimensions or new fundamental objects like strains. Both string theory and loop quantum gravity offer beautiful, mathematically complex pictures of what might be happening at the Planck scale. They are our best maps of this unknown place. Yet, for now, they remain ideas. Without the ability to experiment at the Planck energy, we have no way to know which, if either, is the correct description of reality. We began with a simple rule: to see smaller things, you need more energy. This rule took us on a journey, from the world we can see with our eyes down past cells, molecules, atoms, and quarks. We thought this road might go on forever. But it does not. The universe appears to have a final level. At the Planck scale, the rules of the game themselves change. The energy we use to see becomes a barrier that hides the world from our view. At this boundary, our two greatest stories about reality, general relativity and quantum mechanics, no longer work. The smooth universe of Einstein and the probabilistic world of the quantum collide and fall silent, leaving us with paradoxes and infinities. Space and time, the very foundation of our world, seem to dissolve into a pixelated foam. But this is not an ending. The Planck scale is not a symbol of defeat. It is a challenge. It is the universe telling us that our understanding is still incomplete, that there is a deeper layer to reality waiting to be found. The search for a theory of quantum gravity, whether it is string theory, loop quantum gravity, or an idea no one has had yet, is one of the grandest quests in all of science. It is a quest to write the final chapter in our book of rules, to unite the world of the very large with the world of the very small. The Planck scale is the forbidden boundary where reality stops us from seeing further, but it is also the starting line for the next great leap in our understanding. The universe has a final boundary, and the greatest game we can play is the attempt to understand it. The quest continues. The terrifying truth about empty space. Look out into the night sky. Between the scattered points of starlight and the glow of distant galaxies, there appears to be nothing. For most of human history, we understood this as a simple emptiness, a vacuum. It was seen as the cold, silent stage where the events of the cosmos unfold. A baseline of existence. If you could remove every atom, every particle, every trace of light, you would be left with a perfect and unchanging void. But this understanding is not just incomplete. It is the opposite of the truth. The classical idea of empty space has been replaced by something far more complex, more active, and more unsettling. If you could look past the scale of galaxies and atoms, down to the fundamental structure of reality itself, you would not find silence. You would find constant, energetic activity. The vacuum of space, the nothing that seems to separate everything, is in fact a field of restless energy. A place where particles emerge and vanish in timescales too short to comprehend, challenging our ideas of what it means for something to exist. These are not metaphors. They are the conclusions drawn from the most rigorously tested theories in science. The empty space all around us, and the space between you and this screen, is not empty. It holds a phantom energy and ghostly matter, and its existence presents one of the single greatest mysteries in all of physics. This is the quiet truth of what lies hidden in the void. If this kind of calm exploration into the universe's biggest questions helps you think, consider liking the video and subscribing to the channel. We are about to journey into the heart of nothingness, and what we find there may change how you see everything. The end of emptiness and the rise of the field. Our journey begins with a shift in perspective. For centuries, the universe was seen through a mechanical lens, one envisioned by Isaac Newton. It was a universe of objects, planets, stars, cannonballs, that exerted forces like gravity on one another across an empty, passive space. Space itself did nothing, it was only the container. This tidy picture began to fray in the 19th century. The cause was the invisible force of electromagnetism. Scientists like Michael Faraday, studying magnets, imagined lines of force extending into the space around them. When iron filings are sprinkled over a magnet, they arrange themselves into patterns without touching it. They are responding to something in the space around the magnet. This something was what Faraday called a field. A physical quantity with a value at every point in space and time. It is a property of space itself. The magnetic field is not a stream of particles, but a continuous tension in the fabric of space. When James Clerk Maxwell later unified electricity and magnetism, he described light as a wave moving through this electromagnetic field. This was a revolution. Suddenly, space was no longer a passive backdrop. It could carry fields, have properties, and host waves of pure energy. The nothing of the vacuum had to contain these fields. But the true change, the one that would turn the vacuum into a place of subtle violence, came with the birth of quantum mechanics. When physicists merged the concept of the field with the rules of the quantum world, they created what is now the foundation of modern physics, quantum field theory. Quantum field theory, or QFT, makes a remarkable claim. It suggests the universe is not made of particles but of fields. There is an electron field, a quark field, and a photon field for light. What we perceive as a particle, an electron or a photon, is just a localized vibration, or an excitation, in its underlying field. The entire universe is like a vast, calm lake. This lake represents a field in its lowest energy state, the vacuum. If you tap the lake's surface, you create a ripple that can travel across it. That ripple is what we call a particle. So, an electron is not a tiny solid object. It is a ripple in the electron field. A photon of light is a ripple in the electromagnetic field. This concept is significant on its own. But it is when we ask what happens to these fields in so-called empty space that a more unsettling truth begins to emerge. Classical physics would expect that if there are no particles, the fields should be perfectly flat and still. Quantum mechanics, however, has a very different idea, rooted in one of the most fundamental principles in all of science: the quantum jitter and the law of uncertainty. That principle is Werner Heisenberg's uncertainty principle. It is often stated as a limit on knowledge. You cannot know both the precise position and the precise momentum of a particle at the same time. This is not just a limit on measurement, but a statement about the nature of reality. A particle simply does not possess a perfectly defined position and momentum simultaneously. There is another form of this principle that is even more profound. It states that you cannot know both the precise energy of a system and the precise amount of time it has that energy. For very short intervals of time, there is a great deal of uncertainty in the amount of energy present. Let us consider what this implies for our empty vacuum. According to quantum field theory, the vacuum is the lowest possible energy state of all quantum fields, the ground state. Classically, this lowest energy should be exactly zero. A perfect, unchanging nothing. But the energy-time uncertainty principle forbids this. If the energy of the vacuum were exactly zero and remained so forever, we would know its energy, zero, with perfect certainty. According to Heisenberg, that is impossible. To satisfy the laws of quantum mechanics, the energy at any point in space, even in a total vacuum, cannot be precisely zero. It must fluctuate. For incredibly brief moments, the energy at a point in space can rise, as long as it returns to the average just as quickly. Space is never truly at rest. It is constantly jittering, constantly fluctuating. This unavoidable churning of energy in the vacuum is what physicists call quantum fluctuations. Imagine a perfectly still lake. That is the classical vacuum. Now, imagine a quantum lake. Even at its calmest, its surface is never truly flat. It is always fizzing with tiny, momentary ripples that appear from nowhere and vanish just as quickly. This is what the vacuum of space looks like at the most fundamental level. It is not empty and static, it is a restless sea of energy. This is a core prediction of quantum field theory. Empty space must be filled with this simmering energy, known as zero-point energy. It is the minimum possible energy a quantum system can have, and it is not zero. Even at absolute zero temperature, where all thermal motion should stop, systems still possess this fundamental quantum jitter. Liquid helium, for example, will not freeze solid at standard pressure, no matter how cold it gets, because its zero-point energy is enough to keep its atoms in motion. The vacuum of space is the ultimate quantum system. And so, it too must possess this zero-point energy. Every quantum field that permeates the universe, the electron field, the photon field, the Higgs field, contributes its own zero-point energy to the vacuum. This leads to an inescapable conclusion: the vacuum is not empty. It is a plenum, filled with the latent energy of all potential particles. And from this simmering energy, things can, and do, emerge from nothing. Ghosts in the machine, the reality of virtual particles. The energy from quantum fluctuations is not just an abstract number. For fleeting moments, this borrowed energy can manifest as particles. This is the strange world of virtual particles. According to the uncertainty principle, for an incredibly short time, a packet of energy can emerge from the vacuum. And through Einstein's equation, E equals mc squared, we know energy can be converted into mass. If enough energy fluctuates into existence, It can create a particle-antiparticle pair, such as an electron and its antimatter counterpart, a positron. These particles are called virtual because their existence is borrowed. They are born from the vacuum, exist for a fraction of a second on borrowed energy, and then annihilate each other, returning that energy to the vacuum. The process happens so quickly that the law of conservation of energy is not violated over any measurable timescale. It is useful to think of virtual particles not as tiny solid balls, but as the fluctuations of the quantum fields themselves, the momentary ripples on the quantum lake. While they cannot be observed directly, their effects are real and measurable. They are not just mathematical constructs. They are a fundamental part of how reality functions. The vacuum, therefore, is not a void but a quantum foam, a term from the physicist John Wheeler. At the smallest possible scales of space and time, spacetime itself is no longer smooth, but a chaotic foam of virtual particles being created and annihilated at an unimaginable rate. These ghostly particles also mediate the fundamental forces of nature. The electromagnetic force, the reason two electrons repel each other, can be described as the exchange of virtual photons between them. The two electrons interact by exchanging these force-carrying particles, which exist only for a moment. These are not phantom particles with no consequence. They are essential to the fabric of reality. This raises a pressing question. If empty space is truly this active field of appearing and disappearing particles, how can we prove it? How do you measure the effects of something that exists for less than a trillionth of a second? It sounds like a purely theoretical idea. But it is not. There is a way to see the shadows these ghosts cast. The proof: squeezing nothing and seeing a force. For decades, the idea of a quantum vacuum filled with virtual particles was a theoretical concept. It seemed impossible to test. The answer came not from trying to see the particles themselves, but from manipulating the space where they could exist. The breakthrough was a thought experiment from the Dutch physicist Hendrik Casimir in 1948. Imagine two perfectly smooth, uncharged metal plates, placed in a perfect vacuum, parallel to each other and incredibly close together. According to classical physics, nothing should happen. There is no electrostatic force and no air pressure. They should remain motionless. But Casimir realized that if the quantum vacuum was real, something extraordinary would occur. He considered the virtual particles, specifically virtual photons, appearing everywhere in space. These virtual photons come in all possible wavelengths. However, the space between the two plates acts as a resonant cavity. It restricts which virtual photons can exist there. Only virtual photons whose wavelengths fit a whole number of times into the gap are permitted. Longer wavelength virtual photons simply do not fit. Outside the plates, there are no such restrictions. The open vacuum can host virtual photons of all possible wavelengths. The result is an imbalance. There are more modes of the quantum vacuum, and therefore more virtual particles, on the outside of the plates than on the inside. This imbalance creates a pressure difference. The activity of virtual particles outside the plates exerts a greater pressure than the slightly calmer field between them. This pressure difference pushes the two plates together. This predicted force, arising purely from the fluctuations of empty space, is known as the Casimir effect. It is a tiny force, but a real one. A force from nothing. For nearly 50 years, the Casimir effect remained a theoretical curiosity. The force was predicted to be incredibly weak, and the challenge of engineering the experiment was immense. But in 1997, Stephen Lamoureux at the University of Washington measured the tiny attractive force between a sphere and a plate, and his results matched Casimir's predictions to within 5%. It was a landmark achievement. The vacuum was not empty. Lamoureux had measured a force generated by nothingness, and subsequent experiments have confirmed the effect with even greater precision. The Casimir effect is not the only proof. Another phenomenon, the Lamb shift, shows that the electron in a hydrogen atom is constantly being jostled by the sea of virtual photons in the vacuum. This interaction slightly shifts the electron's energy levels in a way that is measurable and precisely predicted. These experiments transformed the quantum vacuum from a theoretical abstraction into a physical reality. The empty space around us is a physical medium that can exert real forces. And this is where the truth about empty space goes from being a curious feature of physics to a genuinely profound problem. The vacuum catastrophe, the biggest problem in physics. We have established that the vacuum is filled with a baseline energy, the zero-point energy. The Casimir effect and the Lamb shift prove this energy is real. The next logical question is, how much energy is there? This is the question that has created one of the deepest puzzles in science. When physicists try to calculate the total energy density of the vacuum, the answer they get is so wrong it has been called the worst theoretical prediction in the history of physics. The calculation is, in principle, straightforward. One takes all the known quantum fields and sums up the zero-point energy from all their possible modes of vibration. The problem is that there is a near infinite number of possible modes. When you sum all this energy, the resulting number for the energy density of the vacuum, the amount of energy in every cubic centimeter of space, is astronomically large. The predicted value is larger than what we observe by a staggering margin, a number so vast it defies easy comparison. If the vacuum really had this much energy, its gravitational effect would have been so immense that it would have curled the universe into a point an instant after it began. Stars and galaxies could never have formed. The very existence of our large, old, and relatively flat universe is the strongest evidence that this calculation is deeply wrong. And yet, the theories that produce this number, quantum field theory and general relativity, are the two most successful pillars of modern physics. On this crucial point, they clash with a violence that makes no sense. This discrepancy is known as the cosmological constant problem, or the vacuum catastrophe. Then, in 1998, astronomers studying distant supernovae found that the expansion of the universe is accelerating. Something is pushing spacetime apart, acting as a kind of anti-gravity. This mysterious influence was named dark energy. According to Einstein's theory of general relativity, the energy of the vacuum itself would have exactly this effect. It seems we have found the vacuum energy driving the cosmic acceleration. The problem is the amount. When cosmologists measure the strength of this acceleration, they can calculate the actual energy density of the vacuum. It is not zero. It is a tiny, positive value. But this measured value is smaller than the value predicted by quantum theory by an incomprehensible degree. This is the heart of the mystery. It is not just that theory gives a large number and observation gives a small one. It is that the prediction is almost infinitely large, while the observation is almost zero, but not quite. It is as if some unknown physical principle is canceling out nearly all of the vacuum energy with breathtaking precision, leaving only a tiny remnant behind. Why? What fine-tunes the universe with such accuracy? We do not know. This is arguably the deepest unsolved problem in all of physics. The fabric of space is the site of the greatest conflict in modern science. It should be an inferno of energy, but something has suppressed it, leaving only a faint whisper that is slowly pushing our universe apart. Tinkering with the void and staring into the abyss. The vacuum catastrophe has been a source of frustration for decades. But recent work in both theory and experiment is beginning to explore the nature of the void in new ways. Scientists are no longer just measuring the static effects of the vacuum. Some are learning to actively manipulate it, exploring how shaping surfaces at the nanoscale can alter the Casimir force, perhaps for use in future nanotechnologies. More dramatically, some theoretical work has proposed that ultra-intense lasers could stir the vacuum. The idea is that if you focus powerful laser beams on a single point, their combined electromagnetic fields could become so strong that they jolt virtual particle pairs, causing them to scatter and create a real photon, a flash of light from apparent nothingness. This remains a frontier of experimental physics. Perhaps the most unsettling idea comes from the concept of false vacuum decay. Our understanding of the Higgs field suggests that our current vacuum might not be in its true, absolute ground state. It might be in a false vacuum, a state that is stable for now, but not fundamentally stable. Think of a ball resting in a small divot on the side of a large hill. It is stable, but if it gets nudged out, it will roll to the bottom of the hill, to a much lower and truer state of stability. The theory suggests our universe might be in such a state. It is possible that somewhere, a random quantum fluctuation could be large enough to nudge a patch of vacuum into the true vacuum state. This would create a bubble of true vacuum that would expand at the speed of light. Inside this bubble, the laws of physics would change. The properties of fundamental particles, the mass of an electron, the strength of chemical bonds, would be completely different. Structures like atoms and planets would be instantly destroyed. Most physicists believe our vacuum is likely stable on timescales far longer than the current age of the universe. But the mere possibility exists. It is a reminder that the seemingly inert vacuum around us may hold deep and dynamic secrets. The silent void is none of those things. It is the source of a force that proves its own existence. It is the stage for the biggest disagreement in the history of science. And it is a simmering field of potential that might not even be in its final form. The nothing of space is, in fact, one of the most mysterious and active somethings in the entire universe. The universe is so much stranger than we often imagine. The very ground of being, the vacuum we take for granted, is a frontier of discovery that challenges what we think we know. If this journey into the heart of nothingness has sparked your curiosity, please consider liking this video and subscribing for more explorations into the deepest mysteries of the cosmos. And I am curious, what do you think is the solution to the vacuum catastrophe? What is hiding in the structure of reality? Let me know your thoughts in the comments below. We began with a simple image, the silent emptiness between the stars. We end with the realization that this emptiness is an illusion. The vacuum is a physical entity, buzzing with the energy of quantum fields and boiling with the fleeting existence of virtual particles. We learned that this is not speculation. The Casimir effect provides measurable proof that a force can arise from nothing, a pressure from the quantum activity that rages in all of space. The Lamb shift shows us that the properties of atoms are shaped by their dance with this ghostly sea. But this revelation has left us with the most profound puzzle in all of physics, the vacuum catastrophe. Our best theories predict an energy for space that is so large it should have destroyed the universe, yet what we observe is a value so exquisitely small it seems impossibly fine-tuned. It suggests a gap in our understanding that is as vast as the cosmos itself. The quiet truth about empty space is that it is the engine of our greatest questions. It holds the secret to the accelerating expansion of our universe, and perhaps the key to its ultimate fate. It is a reminder that even in the places we expect to find absolute nothing, the universe has hidden a reality of unimaginable complexity. The space you are moving through right now is not empty. It is the energetic heart of a cosmic mystery we have only just begun to unravel. The universe is a lie, Spacetime Foam explained. Look around you. Take a moment to notice your hands, the screen you are watching this on, the space you are in. It all feels solid, continuous, real. Our entire understanding of the cosmos, from the fall of an apple to the slow dance of distant galaxies, rests on the idea that spacetime is a smooth, unbroken fabric. It is the stage on which the story of the universe is written. But what if this smoothness is not the whole story? What if the most fundamental aspect of our world, the very canvas of reality, is an illusion? What if, when we look closer, far beyond what any instrument can see, this calm and predictable stage dissolves into a chaotic, bubbling sea of pure uncertainty? This is not a flight of fancy. This is the theory of spacetime foam. It suggests that at the bottom of everything, the universe is not calm and ordered, but a turbulent, unpredictable frenzy. It tells us that the solid ground beneath our feet is a kind of mirage, and that just beneath the surface, reality itself is boiling. For over a century, physics has been guided by two great theories. They describe the universe with breathtaking accuracy, yet they fundamentally disagree with one another. They are the twin pillars of our modern world, and they present a deep and quiet contradiction. One of them must be incomplete. Or, something far stranger must be true. This is a journey into that contradiction, and the remarkable idea that might resolve it, rewriting our understanding of reality along the way. The Great Divide: Einstein's dream versus the quantum world. In one corner, we have the theory that governs the large-scale universe, general relativity. This is Albert Einstein's masterpiece, a description of the cosmos of profound elegance. It reimagines our understanding of gravity, not as a mysterious force, but as a feature of the universe's geometry. Imagine space-time as a vast, taut sheet. A heavy object, like a star, will cause this sheet to curve. A smaller object, like a planet, moving nearby, will simply follow that curve. It is not being pulled by the star. It is following a path along the bent fabric of space-time. This is gravity. It is not a force, but geometry in motion. And this theory has been stunningly successful. It predicted the bending of starlight around the sun, which has been observed. It predicted that time runs slower in stronger gravitational fields, a fact that GPS systems must account for every second. It also predicted the existence of gravitational waves, ripples in spacetime itself, which were first detected in 2015 and announced to the world in 2016, a century after Einstein imagined them. General relativity paints a picture of the universe that is smooth, continuous, and predictable. It is a cosmos of elegant curves and graceful paths. But then, in the other corner, we have the theory that governs the microscopic realm, quantum mechanics. If general relativity is a classical ballet, quantum mechanics is a world of quiet, counterintuitive rules. It governs atoms and the particles within them, and it operates on principles of probability and uncertainty. In the quantum world, particles do not have fixed locations until they are measured. They exist in a haze of possibility, a superposition of all their potential states at once. An electron is not a single point, but a cloud of potential places it could be. And particles can become entangled, linked in a way that measuring one instantly influences the other, even if they are on opposite sides of the universe. The core of this world is uncertainty. Werner Heisenberg's famous uncertainty principle is not a limit of our tools. It is a fundamental property of reality itself. It tells us that there is a cosmic trade-off. You can know a particle's position, but its momentum will become uncertain. Or you can know its momentum perfectly, but its position becomes a blur. The quantum world is not deterministic, it is probabilistic. It is a realm of jittery, subtle, and fundamentally uncertain behavior. And here is the deep puzzle in modern physics. Both of these theories are correct in their own domains. General relativity perfectly describes the universe on the grandest scales. Quantum mechanics perfectly describes it on the smallest. They are two of the most successful ideas in human history. But they cannot both be the complete story. When you try to apply them to the same event, their mathematics breaks down into infinities and contradictions. This happens in two very important places: at the heart of a black hole, and at the very beginning of the universe. To understand these moments, where immense gravity meets infinitesimal scales, a new theory is needed, a theory of quantum gravity. For decades, the search for this theory has been one of the greatest quests in physics. This is where our story truly begins, with a physicist who dared to look into the divide between these two worlds and imagine what might lie within it. The core analogy, a cosmic ocean. To understand the idea that attempts to bridge this gap, we do not need to begin with complex mathematics. We can begin with an ocean. Imagine you are in a satellite, high above the Earth. From this distance, the Pacific Ocean appears to be a perfect, glassy sheet of blue. It looks uniform, continuous, and calm. This is the universe of our everyday experience, the smooth and predictable world of our classical intuition. Now, imagine you are in an airplane, flying thousands of feet above that same ocean. The surface is no longer a perfect sheet. You can see the gentle, rolling swells of waves, the large-scale patterns on the water's surface. This is the universe of general relativity. We see the large, gentle curves in spacetime created by planets and stars, but the overall fabric still appears smooth and unbroken. Next, you descend into a boat on the water's surface. Now, your perspective changes. You feel the chop of the waves and see the spray. The water is no longer a single, smooth thing, but a dynamic and energetic surface. But what if we could go even deeper? What if we could shrink down to the size of a single molecule of water? At that scale, the idea of a surface would disappear entirely. You would find yourself in a world of chaotic motion, with molecules moving in every direction in a turbulent, swirling, frothing mess. This is the core analogy for spacetime foam. Physicists believe that spacetime itself might behave this way. From our large-scale perspective, it looks smooth and continuous, like the ocean from a satellite. Einstein's theory describes the gentle waves we can see from the plane. But the theory of spacetime foam suggests that if we could zoom in to an unbelievably small scale, we would find a turbulent, chaotic, bubbling reality. The smooth fabric we call spacetime would dissolve into a roiling, frothing sea. This is the idea of spacetime foam. The birth of an idea, John Wheeler's quantum cauldron. In the mid-20th century, one physicist in particular was captivated by this quiet conflict between Einstein's smooth world and the quantum world's uncertainty. His name was John Archibald Wheeler, a brilliant thinker who had worked with Einstein and had a gift for coining phrases that captured profound physical ideas. He helped popularize terms like black hole and wormhole. And in 1955, he gave us another, quantum foam. Wheeler was not simply guessing. He was following the logic of our two best theories to their natural conclusion. His reasoning followed a beautiful chain of thought that connects the quantum world to the fabric of the cosmos. It starts with Heisenberg's uncertainty principle. As we have seen, there is a fundamental limit to how well we can know certain pairs of properties. The one that matters here relates energy and time. The principle allows for a tiny amount of uncertainty in the energy at any point in space, as long as it exists for a very short moment. This means that empty space is not truly empty. The vacuum of space is, in fact, a seething cauldron of activity. Thanks to this energy uncertainty, the universe can borrow a tiny amount of energy from the void for a brief instant. With that borrowed energy, it can create pairs of virtual particles, a particle and its antimatter twin, which pop into existence, exist for an unimaginably short time, and then annihilate each other, paying back the energy they borrowed. This is happening everywhere, all the time, in every cubic centimeter of the space around you. Here is the crucial link. Wheeler knew from Einstein's equation, E equals mc squared, that energy and mass are two sides of the same coin. He also knew from general relativity that energy and mass warp spacetime. So, he asked the critical question: if these virtual particles have energy, even for just a moment, what effect must they have on the spacetime around them? The answer is that they must be warping it. Every time a pair of virtual particles flashes into existence, it should create a minuscule, fleeting disturbance in the fabric of spacetime. Under normal circumstances, these disturbances are so small and so brief that they are completely negligible. But Wheeler pushed the idea to its absolute limit. He asked what happens at the smallest possible scale we can imagine. This is a scale known as the Planck length, which is incomprehensibly small, about 1.6 times 10 to the minus 35 meters. To put that in perspective, if you were to magnify a single atom to be the size of the entire observable universe, the Planck length would be about the height of a single tree. It appears to be a fundamental limit of reality itself. Any attempt to observe something this small would require so much energy that you would instantly create a tiny black hole. Wheeler realized that at the Planck length, and over the equally tiny Planck time, about 10 to the minus 43 seconds, the energy fluctuations from virtual particles could become enormous. The energy being borrowed from the vacuum would become so immense that the tiny disturbances in spacetime would become violent, chaotic ruptures. At this scale, spacetime would no longer be a smooth sheet. The constant creation and annihilation of high-energy virtual particles would churn the fabric of geometry into a chaotic, bubbling, foamy mess. The very concepts of distance and duration would lose their meaning. This is what John Wheeler called spacetime foam. It is the point where the smooth geometry of Einstein's universe is shattered by the deep uncertainty of the quantum world. It is the bottom floor of reality, and it is a world of constant fluctuation. The hunt for the foam, chasing shadows in the cosmos. This idea is remarkable. But is it real? Is the universe truly a chaotic foam at its foundation? Or is this just a beautiful piece of mathematical thinking? Physics is not just about imagining ideas, it is about testing them. And for decades, scientists have been on a quiet, cosmic detective mission, hunting for the subtle fingerprints that this foam might have left on the universe. The central challenge is clear. We cannot build a microscope powerful enough to see the Planck scale. It is so far beyond our reach that direct observation is out of the question. So, physicists had to think of a different approach. They realized that if they could not go to the foam, they had to look for ways the foam might come to them. The main strategy has been to look for a very specific, subtle effect the foam might have on light that travels across vast cosmic distances. The key idea involves a potential violation of one of the bedrock principles of physics, Lorentz invariance. That is the formal name for the rule that the speed of light in a vacuum is constant for all observers, no matter their motion or the light's energy. It is a cornerstone of Einstein's theory of relativity. But if spacetime is a foam, this principle might not be absolute. Imagine light traveling not through a perfect vacuum, but across that chaotic, foamy ocean. A high-energy photon, like a gamma ray, is like a small, fast boat. A low-energy photon, like a radio wave, is like a massive cruise ship. On a perfectly calm sea, both would travel at the same speed. But on a choppy, foamy ocean, the small boat would be tossed around more by the small waves, its path minutely jostled and delayed with every bubble it encounters. The massive cruise ship, however, would plow through the small-scaled chop almost unaffected. Physicists reasoned that if spacetime foam exists, something similar should happen to light. High-energy photons should interact more with the tiny bubbles in the foam than low-energy photons. Over a short distance, this effect would be undetectable. But if the light traveled for billions of light years, these tiny, infinitesimal delays could add up. The prediction was clear. If you observe a powerful event far across the universe that releases light of all energies at once, the high-energy gamma rays should arrive just a fraction of a second later than the low-energy radio waves. So, the hunt was on. Astronomers needed a kind of cosmic lighthouse, an incredibly powerful, distant explosion that releases photons of all energies at the same time. The perfect candidates are gamma-ray bursts, GRBs, some of the most violent and energetic events in the universe, visible from billions of light-years away. Several observatories were suited for this mission. Telescopes like NASA's Fermi Gamma Ray Space Telescope, the Chandra X-ray Observatory, and ground-based arrays like Veritas stared at these distant explosions, ready to time the arrival of their light with exquisite precision. They were looking for that telltale signature, a delay that depended on the energy of the photon. And the verdict came in. The results were stunning, but not in the way many had hoped. The telescopes saw nothing. Light from gamma-ray bursts that had traveled for billions of years showed no discernible time lag. High-energy photons and low-energy photons arrived at essentially the same instant. From one event to the next, the result was the same. Spacetime appeared to be stubbornly, frustratingly smooth. These observations have placed incredibly tight constraints on the theory. They do not disprove the idea of spacetime foam entirely, but they do tell us that if it exists, it is far less foamy than the simplest models predicted. The bubbles in spacetime must be much smaller or interact with light far less than was originally thought. It is like looking at the ocean and finding that the surface is calm even when you get incredibly close, pushing the scale of any potential turbulence down into an even more inaccessible place. Spacetime, at least down to a distance 1,000 times smaller than the nucleus of a hydrogen atom, appears to be smooth. The cosmic ocean is eerily calm. So if our most powerful telescopes, looking across billions of light years, have found no evidence of this cosmic turbulence, is the idea a dead end? A beautiful concept that is simply not true? The story does not end here. The lack of evidence has forced physicists to think in even more creative ways about what the fundamental nature of spacetime might be. The journey gets much deeper. And while we take a moment before diving into these even stranger realities, if this kind of calm exploration into physics helps you unwind, consider liking the video and subscribing to the channel. Your support helps us explore these quiet, deep questions, and you will not want to miss where we are going next. Beyond the foam, new physics and deeper realities. The null result from the gamma-ray telescopes was a disappointment for some, but in science, a negative result is often more interesting than a positive one. It did not end the idea that spacetime has a quantum nature. It just told us that our first guess about what it looks like was likely too simple. It forced physicists to go back and consider more sophisticated, and frankly, more mind-bending possibilities. If spacetime is not a simple foam, then what is it? This question has led us to the forefront of theoretical physics, to ideas that propose even more radical views of reality. One of the leading contenders is a theory called loop quantum gravity, or LQG. This theory takes the idea of quantum spacetime to a new level. It proposes that spacetime is not continuous at all. It is not a smooth fabric that gets foamy at small scales. It is fundamentally discrete from the very beginning. Imagine spacetime as a piece of cloth. The original foam idea is that the cloth itself is smooth, but it is bubbling and fizzing. Loop quantum gravity says there is no cloth. Instead, reality is woven from a network of finite, indivisible loops. These loops connect at nodes, forming what are called spin networks. In this view, space is not empty, it is made of these networks. A node represents a tiny, quantized chunk of volume, like a single pixel of space. A link represents a quantized area connecting these volumes. There is nothing smaller. You cannot have half a pixel. Space itself is atomic. The evolution of these networks over time is what is called a spin foam. In this picture, the foam is not a chaotic bubbling in spacetime. It is the quantized, granular structure of spacetime itself. Then there is the other major contender for a theory of everything, string theory. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, one-dimensional vibrating strings. What we perceive as different particles, an electron, a photon, a quark, are all just different vibrational modes of the same fundamental string, like different notes played on a single string of a guitar. String theory requires the existence of extra, hidden dimensions of space beyond the three we experience. In this framework, spacetime foam could arise from the complex interactions of these strings and the higher dimensional surfaces they can form. The quantum jitters of these strings vibrating in hidden dimensions could manifest in our familiar dimensions as the foamy, uncertain texture of spacetime. However, like LQG, string theory is a work in progress, with many different versions and no definitive experimental proof. Perhaps the most reality-shattering idea to emerge from these investigations is the holographic principle. First proposed in the context of black holes, this principle is as profound as it is strange. It suggests that all the information contained within a volume of space, every particle, every field, every bit of data that makes up you and the room you are in, can be completely described by the physics happening on the two-dimensional boundary of that volume. In other words, you might be a hologram. The universe we perceive as three-dimensional might be a projection of information encoded on a distant 2D surface. How does this connect to spacetime foam? The foam could be a consequence of this holographic projection. The pixels on that 2D surface would correspond to the Planck length, representing the fundamental resolution limit of reality. The quantum fluctuations on that 2D surface would project into our perception as the three-dimensional, chaotic bubbling of spacetime foam. Our universe would be, in a very real sense, a grainy hologram, with the foam being the artifact of its limited resolution. These theories, loop quantum gravity, string theory, and the holographic principle, are all attempts to build a bridge across the Great Divide. They are all mathematically complex and, as of now, unproven. But they all point toward the same, radical conclusion that John Wheeler first suspected. The smooth, continuous universe we see is not the fundamental reality. The implications: if the foam is real, what is reality? Let us take a step back. We have journeyed from a quiet conflict between two great theories, down to the theoretical bubbling of the Planck scale, and through the unfamiliar landscapes of modern physics. It is easy to get lost in the details of gamma-ray bursts and spin networks. But what does it all mean? If any of these ideas are even remotely correct, the implications are not just academic. They strike at the very heart of our perception of existence. First, it would mean the end of continuity. For all of human history, we have perceived the world as smooth and unbroken. We assume we can divide space and time infinitely. Spacetime foam suggests this is an illusion, an artifact of our large scale. If spacetime is quantized, like in loop quantum gravity, or foamy at its base, then space and time are not fundamental. They are emergent properties. They are grainy and pixelated at their core. The idea of a specific point in space or a precise instant in time might be meaningless at the fundamental level. Reality is not a high-definition movie. It is more like a digital image with a finite resolution, and the foam is the pixelation you see when you zoom all the way in. The implications become even more profound. John Wheeler's original idea of the foam included the possibility that on rare occasions, these quantum fluctuations could be so violent they could pinch off a piece of space-time, birthing a new, baby universe. Our own universe could have begun as just such a fluctuation in a pre-existing cosmic foam, one bubble among an infinite sea of other bubbles in a vast multiverse. The Big Bang might not have been the beginning of everything, but simply the moment our bubble started to expand. This idea completely redefines our concept of nothing. The vacuum is not empty. It is a place of seething potential, a quantum cauldron bubbling with virtual particles and geometric fluctuations. The foam is not something that exists in space and time. It is the primordial state of space and time itself. The laws of nature might not be eternal, unchanging truths, but rather the stable, large-scale patterns that crystallize out of the underlying chaos of the foam, just as the intricate, stable patterns of a snowflake emerge from the chaotic jiggling of water molecules. This journey quietly challenges our sense of what is real. The solid chair you are sitting on is almost entirely empty space, held together by invisible fields. The light hitting your eyes behaves as both a particle and a wave. And now, the very spacetime that contains all of this might itself be a statistical average of a deeper, frenzied quantum reality. We may be living on the calm surface of an unimaginably deep and turbulent ocean, mistaking the surface tension for solid ground. The universe is not the steady, predictable stage we once thought it was. It may be an emergent property, arising from a foundation of pure chaos and probability. We began with a contradiction, a quiet disagreement between the two most successful theories in the history of science. We followed the intuition of John Wheeler, who looked into that conflict and saw not a problem, but a revelation. A universe that, at its smallest scale, dissolves into a froth of quantum uncertainty. We became cosmic detectives, searching for the echoes of this foam in the light from distant explosions, only to find an unnerving smoothness that pushed the mystery even deeper. And this led us to the very frontiers of human thought, to ideas like loop quantum gravity, string theory, and the holographic principle, each proposing its own radical reimagining of space and time. The theory of spacetime foam, in all its forms, represents more than just a potential solution to a physics problem. It is a profound statement about our place in the cosmos. It tells us that the familiar, continuous, and predictable world we inhabit is an emergent phenomenon, a gentle illusion created by scale. It suggests that beneath the serene facade of the cosmos lies a foundation of pure, untamed chaos. The very fabric of reality may not be a solid bedrock, but a turbulent, quantum sea. We do not have the final answer. The hunt for evidence continues. But the question itself has forever changed our perspective. The ground beneath our feet may never feel quite as solid again. For if our reality is just the calm surface of a turbulent quantum sea, what other secrets are hiding in the deep? The universe is pixelated and we can prove it. When you look around, the world seems to flow. Time passes in a quiet stream, and you move through space without any obvious jumps or interruptions. It feels solid and continuous. For centuries, this smooth reality was accepted as a fundamental truth. Our understanding of the cosmos was built upon it. A grand, predictable stage where the laws of nature played out with perfect consistency. But this comforting picture, it turns out, may only be an illusion. A breathtakingly high-resolution one. Some physicists now suspect that if you could zoom in, far beyond the scale of atoms and the frantic movement of quarks, you would find the fabric of space and time is not smooth at all. They propose it might be pixelated, composed of indivisible, fundamental units, like a digital image on a screen. And because of those pixels, our reality might be fundamentally blurry. Your exact position in the universe, at any given moment, may never be truly certain. This isn't just a thought experiment. This is the frontier where our two greatest theories of reality appear to contradict each other. And one possible way forward is to reconsider our most basic ideas about space, time, and existence itself. It is a working hypothesis that the universe is pixelated, and we are now developing experiments that may one day be able to test it. The smooth illusion. To understand how different this idea truly is, we first have to appreciate the picture it is replacing. For more than 200 years, our vision of the cosmos was shaped by a single figure, Isaac Newton. In his world, space was an absolute, unchanging stage. An infinite, three-dimensional grid, eternally fixed. Imagine a vast, empty room. The walls, floor, and ceiling represent the dimensions of space. Whether you place a marble or a star inside that room, the structure of the room itself remains unchanged. This was Newton's space, a rigid, passive background. Time, for Newton, was just as absolute. It was a universal clock, ticking at the same rate for everyone, everywhere. A second on Earth was identical to a second near Jupiter or in a distant galaxy. Time flowed like a great river, carrying everything with it at a constant, unalterable pace. This framework of absolute space and time created a vision of the universe as a magnificent clockwork mechanism. If you knew the position and momentum of every particle, you could, in theory, predict the entire future of the cosmos. It was a deterministic universe, governed by elegant, precise laws. Everything had a definite place and a definite path. There was no fuzziness. The world we perceived with our senses, smooth, continuous, and predictable, was, according to Newton, the world as it truly was. This classical view was dominant for centuries, not because it was stubbornly held, but because it worked. It allowed us to predict the orbits of planets, the paths of cannonballs, and the tides of the oceans. It gave us a sense of order. The universe was a grand, intelligible machine, and we were beginning to understand how it functioned. The idea that this smooth, continuous stage could be anything but fundamental was not a serious consideration. It was the bedrock of physics. But this beautiful, orderly universe was about to be re-examined by a revolution that would redefine space and time forever. A revolution sparked by a young patent clerk who dared to imagine a world where the stage itself was part of the performance. Einstein's revolution. At the dawn of the 20th century, Albert Einstein looked at Newton's rigid stage and began to see it differently. His theories of relativity didn't just adjust the old rules, they offered a new book entirely. The change began with special relativity, which delivered a surprising blow to Newton's universal clock. Einstein revealed that time was not absolute. The rate at which time passes depends on your motion. The faster you move through space, the slower time passes for you relative to someone standing still. This was not a trick of perception, but a fundamental property of reality. The single, universal river of time had fractured into a billion personal streams. But it was his masterpiece, general relativity, that completely changed the view of a static, passive space. Einstein proposed that space and time were not separate, but were woven together into a single, dynamic four-dimensional fabric, spacetime. And this fabric was not rigid, it was flexible and responsive. A common analogy, and a useful one, is a bowling ball on a trampoline. A flat, stretched sheet represents the fabric of spacetime. In an empty universe, it's flat. But place a massive object, like a star, onto the sheet, and it creates a curve. This curvature is what we experience as gravity. A planet orbiting a star isn't being pulled by a mysterious force, as Newton thought. Instead, it's simply following a straight path through curved space, like a marble rolling along the dip created by the bowling ball. This was a remarkable conceptual leap. Gravity was no longer a force acting in space, it was a property of spacetime itself. Mass tells spacetime how to curve, and the curve of spacetime tells objects how to move. The stage had come alive. It was no longer a passive backdrop but an active participant, bending, warping, and even rippling. Einstein predicted these ripples, gravitational waves, could travel across the universe. A prediction confirmed with incredible precision a century later. Einstein had transformed our understanding. He replaced Newton's rigid grid with a dynamic, geometric tapestry. Yet, for all its revolutionary ideas, Einstein's spacetime had one crucial thing in common with Newton's: it was smooth. Infinitely smooth. You could, in theory, zoom into his fabric of spacetime forever and never find a seam or a jagged edge. For a time, it seemed that physics had found its new foundation. General relativity described the universe of the very large, stars, galaxies, the expansion of the cosmos, with flawless accuracy. But at the same time, another, even stranger revolution was taking place, one that would explore the world of the very small. And it would uncover a truth so counterintuitive that it would begin to challenge the very idea of a smooth, continuous reality. The meeting of these two theories would create one of the greatest puzzles in modern physics. The quantum break. While Einstein was reimagining the cosmic stage, other physicists were looking into the world of the atom, and what they found was deeply strange. This was the dawn of quantum mechanics, and it began with a physicist named Max Planck. Planck was studying light from hot objects, and the accepted theories were failing to explain the data. In what he later called an act of desperation, he put forward a new idea. What if energy was not a continuous flow, but came in discrete packets? He called these packets quanta. To understand how different this was, think of a ramp versus a staircase. Classical physics saw energy like a ramp. You could have any value, with infinite possibilities in between. Planck's idea turned the ramp into a staircase. You could be on the first step, or the second, but never on step 1.5. Energy, he proposed, was quantized. At first, this was seen by many as a mathematical trick. But soon, Einstein himself showed that light was made of these energy packets, which we now call photons. The idea grew. Physicists discovered it wasn't just energy that was quantized, matter, too, was fundamentally chunky. Everything, electrons, protons, the forces between them, existed in discrete units. The smooth, continuous world of classical physics was, at the subatomic level, dissolving into something more like a pointillist painting. The strangeness was just beginning. Another giant of the era, Werner Heisenberg, uncovered what is perhaps the most unsettling principle of this new quantum world: the uncertainty principle. He realized there is a fundamental limit to what we can know about a quantum particle. You cannot, for example, simultaneously measure both its exact position and its exact momentum. The more accurately you know its location, the less you can know about its momentum, and vice versa. This was not a limitation of the measuring instruments. It appeared to be an inherent property of reality itself. A particle does not seem to have a single, definite position until it is measured. Instead, it exists as a cloud of probabilities. The quantum world was not a clockwork mechanism, it was governed by the laws of chance. And here lies the great disagreement that has puzzled physics for a century. We are left with two incredibly successful theories of reality that appear to be incompatible. On one hand, we have Einstein's general relativity. It describes a large-scale universe that is smooth, continuous, and geometric. Everything has a precise location in a gracefully curving spacetime. On the other hand, we have quantum mechanics. It describes a small-scale world that is chunky, probabilistic, and uncertain. Nothing has a definite location until it's observed. These two pictures cannot both be the complete truth. They are based on contradictory principles. General relativity says spacetime is a smooth sheet. Quantum mechanics says everything else is made of discrete chunks. So what happens when you try to apply quantum principles to the fabric of spacetime itself? The mathematics begins to break down, producing infinities that signal a deep misunderstanding. If you try to pinpoint a location in space to an infinitely small point, the uncertainty principle suggests the energy there could become infinitely large, creating a microscopic black hole. This tells us that our understanding is incomplete. There is a quiet but profound contradiction at the heart of our description of the universe. This conflict is not just an academic debate. It is what prevents us from understanding the most extreme phenomena in the cosmos: the heart of a black hole, or the very first moments of the Big Bang. To solve this puzzle, to find a more unified theory, physicists need a new idea. An idea that can bridge the gap between the smooth world of Einstein and the chunky world of the quantum. The leading proposal is as simple as it is profound. What if Einstein's smooth fabric is just an approximation? What if spacetime itself is quantized? The pixelated solution. Faced with this deep incompatibility, physicists began to consider a radical possibility. What if the problem was not with either theory, but with a shared, unspoken assumption? What if spacetime is not truly continuous? This is the core idea behind a pixelated universe. The analogy that many physicists use is that of a digital screen. When you look at a high-resolution photograph, it appears perfectly smooth. You see gentle curves and soft gradients. But if you were to magnify that image again and again, you would eventually see that the image is made of a grid of tiny, single-colored squares, pixels. The smooth reality of the image is an emergent property. From a distance, it looks continuous. Up close, its discrete nature is revealed. The proposal is that spacetime itself might be like this. The smooth, curving fabric described by Einstein could be a low-resolution view of a stranger, underlying reality. If we could zoom in to the most fundamental level, we might discover that spacetime is made of indivisible units, the pixels of space and time. This isn't just a vague analogy. There is a specific, mind-bogglingly small scale where this pixelation is thought to occur. It's called the Planck scale. The Planck length, theorized by the same Max Planck who began the quantum revolution, is about 10 to the power of minus 35 meters. It's a number so small it is difficult to comprehend. A single hydrogen atom is a million times larger. It is, in theory, the smallest possible meaningful length. It might be the fundamental resolution of reality, a point beyond which the concepts of space and distance no longer have meaning. Similarly, the Planck time, at 10 to the minus 43 seconds, could be the shortest possible unit of time. If you simply cannot have a distance smaller than the Planck length, then this provides a potential solution to the clash between gravity and the quantum world. The nonsensical infinities in the old theories came from assuming you could divide space into infinitely small points. But if spacetime has a minimum resolution, if it is pixelated, then those infinities naturally disappear. You can't squeeze infinite energy into a point if there are no points, only pixels. The staircase replaces the ramp, and the math begins to make sense again. This idea of a granular spacetime is a cornerstone of several leading attempts at a theory of quantum gravity. One prominent path is loop quantum gravity, or LQG. It describes spacetime not as a background, but as a physical, quantum object woven from a network of finite, interlocking loops. Think of it like a piece of chainmail, where each link is a fundamental quantum of space. When these networks evolve, they create what's known as a spin foam, which represents the quantum structure of four-dimensional spacetime. Another major approach is string theory, which proposes that the fundamental constituents of reality are not particles, but tiny, vibrating strings. Different vibrations of these strings give rise to all the particles and forces we see. While conceptually different, string theory also points to a reality where the smooth continuum breaks down at the Planck scale. These theories, and others like them, all point toward a similar conclusion. The smooth world we perceive may just be a convenient approximation. The fundamental reality could be a discrete, granular, quantum structure. A universe built not on an infinitely divisible canvas, but on a finite set of cosmic pixels. If this is true, the implications for our understanding of reality are quietly staggering. The blurry reality. If the universe is truly pixelated at its core, then the world is not quite what it seems. The consequences of this idea ripple outward, affecting our concepts of position, motion, and even reality itself. It would mean the certainty we take for granted is an illusion, and at the deepest level, our universe is fundamentally blurry. The most direct consequence of a pixelated spacetime is that your position can never be a perfect, geometric point. If space is made of indivisible Planck-scale pixels, then your location can't be specified more precisely than the size of one of these pixels. You are not at a point, you are in a pixel. This is an uncertainty built into the very coordinate system of the universe. This isn't just a theoretical limit, it may be a physical one. Imagine you wanted to build a microscope powerful enough to see something smaller than the Planck length. To do this, you would need a probe, like a photon of light, with an incredibly short wavelength. According to quantum mechanics, a shorter wavelength means higher energy. To probe the Planck length, you would need a photon with an immense amount of energy. But here is the problem, as described by Einstein's theory. If you concentrate that much energy into such a tiny region, it would create a gravitational field so intense it would instantly collapse into a microscopic black hole. Your experiment would be swallowed by the very phenomenon it was trying to measure. It is as if the universe itself prevents us from ever seeing its own pixelation directly. This fundamental blurriness would extend beyond just position. It could affect the very geometry of the cosmos. In general relativity, spacetime curvature defines gravity. But if position is uncertain, then curvature might also be uncertain. At the smallest scales, spacetime might not be a smooth landscape, but a chaotic, probabilistic foam of quantum geometry. This leads to a quiet but profound question. If space and time are discrete, is motion an illusion? In our smooth world, an object moves from point A to B by passing through every point in between. But in a pixelated universe, there are no points between the pixels. Does an object, then, simply jump from one pixel to the next? Is motion a discrete series of appearances, like a character moving across the frames of a film? If this were true, it would imply the universe has a fundamental frame rate. The fastest anything could happen would be to move from one Planck pixel to the next, a process that would take 1 unit of Planck time. This would be the cosmic clock speed, the ultimate refresh rate of reality. Everything we perceive as smooth motion would be a sequence of these incredibly rapid, discrete steps, happening so fast they create the illusion of flow. This blurry, probabilistic, and discrete reality is no longer just an abstract theory. It is a picture that emerges as a possible solution to the collision of our best science. And now, for the first time, we are beginning to devise experiments that could search for evidence to support it. The big picture. The idea of a pixelated universe forces us to confront some of the biggest questions we can ask. If our reality is built from discrete bits of information, governed by a set of underlying rules, it bears a certain resemblance to a sophisticated computer simulation. The pixels of spacetime could be the fundamental bits on a cosmic hard drive. While this remains in the realm of speculation, the physics of a quantized universe provides a framework where such an idea becomes, for the first time, not just philosophical but potentially physical. But beyond such ponderings, the hunt for concrete proof is on. Scientists are actively searching for a telltale sign of this cosmic granulation. One promising avenue involves looking at distant and violent events, such as gamma-ray bursts. These are colossal explosions, billions of light-years away, that release jets of high-energy photons. The idea is that if spacetime is pixelated, its granular structure might subtly affect how light travels. Photons of different energies might interact with the spacetime pixels in slightly different ways. Some theories suggest that higher energy photons, with their shorter wavelengths, might travel ever so slightly slower than lower energy ones. This difference would be undetectable over short distances. But for light that has traveled for billions of years, this minuscule time lag could accumulate into a measurable delay. Telescopes are watching these distant bursts, hoping to find a discrepancy in the arrival times of photons. So far, the results have been inconclusive, but the sensitivity of our instruments improves with each passing year, and the search continues. Other experiments have tried different approaches. The holometer experiment at Fermilab used sensitive laser interferometers to look for a tiny, correlated jitter in spacetime that some models predict. While it did not detect the specific noise it was looking for, it served as a powerful proof of concept, pushing the boundaries of how precisely we can measure the stillness of space. The quest to understand the quantum nature of spacetime is more than an attempt to answer a curious question. It is the central thrust in the search for a more complete theory of physics, one that could finally unite Einstein's gravity with the quantum world. Finding evidence of spacetime quantization would be the first major clue. It would allow us to finally ask what happens in the singularity of a black hole, and to perhaps glimpse the conditions that gave birth to our universe in the Big Bang. We stand at a remarkable moment. The smooth, solid world of our senses, once thought to be absolute, may be a profound illusion. Beneath the surface of our everyday reality could lie a universe far stranger than we once imagined, a cosmic mosaic, shimmering with quantum uncertainty, built not from a continuous cloth but from the fundamental pixels of existence. The journey has taken us from the clockwork perfection of Newton, through the warped fabric of Einstein, to the edge of a new reality, one that may be discrete, probabilistic, and fundamentally blurry. This is no longer a matter of pure philosophy. It is a tangible, testable frontier. With every distant gamma-ray burst we observe, with every new generation of instruments we build, we get closer to an answer. Closer to the evidence that will tell us whether our universe is, indeed, pixelated. The question is not just whether the universe is a picture, but what that picture might be telling us about the nature of everything. The single point in the universe where physics fails. There are ideas in science that feel complete. Albert Einstein's theories of relativity are one of them. For more than a century, they have offered a quiet, elegant way to understand the universe. They describe the gentle wobble in Mercury's orbit and the way starlight bends as it passes the Sun. They foresaw ripples in spacetime itself, gravitational waves, and in confirming their existence, we learned a new way to listen to the cosmos. With a quiet and startling precision, Einstein's equations describe the movements of planets, stars, and galaxies. They are a foundation of modern physics, a profound achievement of human thought. But resting deep inside those equations is a question. A prediction so strange, so unfamiliar, that it suggests the theory itself has a boundary. It predicts that in a single, impossibly small place, the universe we think we know can come to a quiet end. A place where gravity becomes a number too large to write, where matter is pressed into nothing, and where the rules of physics, cause and effect, space and time, seem to fall silent. This place is called a singularity. And it is the one point in the universe where our science, our understanding, and our ability to describe reality appears to break down. This isn't just a theoretical curiosity. According to Einstein's theory, these points are not only possible, but inevitable. They are thought to exist inside every black hole and, most curiously, at the very beginning of our own universe. How can our best map of reality also point to a place where the map ends? What truly happens at this point of final collapse? And what might lie beyond this edge of physics? Today, we begin a journey to that edge of understanding, to the one place in the cosmos where our rules no longer seem to apply, and where the next great scientific story is waiting to be written. A quiet revolution in gravity. To understand this puzzle, we first have to appreciate the idea it seems to undermine: Einstein's general theory of relativity. Before Einstein, our picture of gravity came from Isaac Newton. For more than 200 years, Newton's law of universal gravitation was the final word. Gravity was a force, an invisible pull reaching across space, drawing objects toward one another. It was simple, it felt intuitive, and it worked remarkably well. It could describe the fall of an apple and the orbit of the moon with quiet precision. But as the 19th century ended, small questions began to linger. The most well-known was the orbit of Mercury. Newton's laws couldn't quite explain a small, steady wobble in the planet's path around the Sun. It was off by a tiny amount, just 43 arcseconds per century, but it was a difference that no adjustment to Newton's equations could resolve. It was a loose thread, a hint that something about our picture of gravity was incomplete. Then, in 1915, Albert Einstein offered a different way of seeing. He proposed that gravity was not a force at all. It was a property of the universe's geometry. Imagine a flat, stretched-out sheet. This sheet represents the fabric of the universe, a four-dimensional landscape he called spacetime. With nothing on it, the sheet is perfectly flat. A small marble rolling across it would travel in a perfectly straight line. Now, place a heavy ball in the center of the sheet. The fabric curves and dips around the mass. If you roll the marble again, it no longer moves in a straight line. It follows the curve created by the heavy ball, circling it in what looks like an orbit. The marble isn't being pulled by a hidden force. It is simply moving along the straightest possible path through a space that is no longer flat. This is the essence of general relativity. As the physicist John Archibald Wheeler later said, "Spacetime tells matter how to move. Matter tells spacetime how to curve." This was not just a different story, it was a more accurate one. When Einstein applied his equations to Mercury's orbit, the lingering 43 arcsecond wobble was explained perfectly. The Sun's mass was warping spacetime around it, and Mercury was just following the curved path laid out for it. The loose thread was tied. But general relativity went further. It made other predictions that seemed to stretch the bounds of imagination. It predicted that the immense gravity of an object could bend the path of light. During a solar eclipse in 1919, astronomers watched starlight grazing the sun's edge and found it was deflected by the exact amount Einstein's equations had foreseen. This quiet confirmation made Einstein known around the world. His theory also predicted something called gravitational time dilation, that time itself moves at different speeds in different places. A clock near sea level will tick just a little slower than a clock on a mountaintop. This isn't a mechanical issue with the clock, it's a fundamental quality of time itself. Today, the GPS satellites our phones use must constantly adjust for this. Without general relativity, your GPS location would become wrong by several kilometers every day. And perhaps most profoundly, the theory predicted gravitational waves. If a massive object moves, it should create gentle ripples in the fabric of spacetime, like a stone dropped in a quiet pond. For a century, this was just an idea. Then, in 2015, the LIGO Observatory detected the faint signal of a gravitational wave from two black holes colliding more than 1 billion light-years away. It was a remarkable moment, confirming one of the last great predictions of the theory and opening a new way of observing the universe. From our local solar system to the evolution of the cosmos, general relativity has passed every test we've given it. It is, by all measures, a deeply successful theory of gravity. And yet, this same theory carries the seeds of its own limit. It tells us that if you gather enough mass in a small enough space, the curvature of spacetime doesn't just bend. It breaks. Where the map ends, the journey to the breakdown of physics begins with the end of a star. For most of its life, a star exists in a state of balance. In its core, nuclear fusion creates an enormous outward pressure. This is perfectly matched by the inward pull of the star's own gravity. The star is stable, a point of light held in equilibrium. But for stars much more massive than our Sun, this balance cannot hold forever. In time, the fuel in the core is used up. The furnace grows quiet and cold. Suddenly, the outward pressure fades, and gravity becomes the only influence. In a fraction of a second, the star's core collapses inward. The outer layers are thrown away in a supernova explosion, one of the most powerful events in the universe. But what is left behind is the true subject of our story. If the core that remains is massive enough, about 3 times the mass of our Sun or more, there is no known force that can stop its collapse. It continues to shrink, and shrink, and shrink. According to general relativity, this runaway collapse creates one of the most unfamiliar objects in the cosmos, a black hole. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can leave. The edge of this region is called the event horizon. It is not a solid surface, but a quiet point of no return. Crossing it is like drifting past the edge of a waterfall. Once you are over, no amount of effort can take you back. The current is simply too strong. To someone watching from far away, an object falling toward a black hole seems to slow down as it nears the event horizon. Its light becomes redder and fainter, until it appears to freeze at the edge, fading from view. But for the object itself, nothing special would seem to happen at the event horizon. You would drift across without a jolt. Your fate, however, would be sealed. All possible paths would now lead in only one direction, inward toward the center. And it is here, at the heart of the black hole, that Einstein's theory points to a problem. As the matter of the collapsed star is crushed inward, the equations of general relativity predict it will be squeezed into a space with zero volume. Think about that for a moment. The entire mass of a star, compressed into a region that is not a region at all. A point with no dimensions. This leads to a state of infinite density and infinite gravity. This is a gravitational singularity. In physics, the word infinity is a quiet alarm. It is a sign from the mathematics itself. When an equation returns an infinite value, it often means the theory has been pushed beyond its intended use and is no longer describing reality. It's the mathematics saying, I don't know what happens here. My language doesn't work. It is, in the most literal sense, the point where this description of physics falls silent. To give this a formal name, physicists use a mathematical measure for the curvature of spacetime called the Kretschmann scalar. You can think of it as a kind of curvature meter. In the gentle curves of spacetime around Earth, this scalar has a small, finite value. As you get closer to a black hole, the value grows. But at the place where the singularity should be, the equations show that the Kretschmann scalar becomes infinite. This isn't a mathematical quirk that can be explained away. It is a genuine feature predicted by the theory. It's the mathematical signature of spacetime becoming so warped that it has torn a hole in the fabric of reality. At the singularity, the gravitational field is infinitely strong, and cause and effect are no longer clear. A particle that reaches the singularity simply ceases to have a future within the framework of general relativity. This is the question at the foundation of Einstein's work. The theory that so perfectly describes gravity everywhere else also predicts a point where gravity becomes an absurdity. For many years, physicists, including Einstein himself, felt uneasy about this prediction. They hoped it was an artifact of perfect mathematical models, something that would not happen in the messy reality of a collapsing star. Then, in the 1960s, the work of Roger Penrose and Stephen Hawking showed otherwise. Through a series of mathematical proofs called the singularity theorems, they demonstrated that under general relativity, a singularity is not just a possibility, it's an inevitability. If an event horizon forms, a singularity must be inside. There is no way around it. Penrose's work on this was so foundational it contributed to his share of the Nobel Prize in Physics in 2020. An award he shared with Reinhard Genzel and Andrea Ghez for their work on black holes. So we are left with a quiet paradox. Our best theory of gravity guarantees the existence of points where that same theory can no longer provide answers. It leads us to the edge of a cliff but gives no hint of what lies in the space below. Different kinds of silence. Not all singularities are thought to be the same. The language of general relativity allows for different kinds of black holes, and so, different kinds of singularities. The first and simplest solution was found by Karl Schwarzschild in 1916. It describes a perfectly spherical, non-rotating black hole. At its heart lies the simplest kind of singularity, a point. All the mass is crushed into a single, zero-dimensional point of infinite density. It's a final end. In the real universe, however, almost everything spins. When a massive star collapses, its rotation doesn't just stop. It speeds up, like an ice skater pulling in their arms. This suggests that real black holes should also be spinning. The mathematical description for a rotating black hole is much more complex. It was discovered by Roy Kerr in 1963. A Kerr black hole is different in a few ways, but the most important difference is at its center. According to Kerr's solution, the singularity in a rotating black hole is not a point. It's a ring. This is where the story gets stranger. A ring singularity is a one-dimensional loop of infinite density. Instead of being crushed to a point, matter is squeezed into this infinitely thin, spinning circle. This seemingly small change has puzzling implications. With a point, all paths lead to the same end. There is no through. But with a ring, a theoretical possibility emerges. If an object could fall into a Kerr black hole on a precise path, along the axis of rotation, it is mathematically possible to pass through the center of the ring without hitting the singularity. What happens next? The mathematics suggests passing through the ring could lead somewhere else. Some solutions propose the existence of a wormhole, a theoretical tunnel to another part of our universe or even another universe entirely. This idea has, of course, become a familiar one in science fiction. But before we imagine a journey through a black hole, there are a few very real problems. First, the other side of this theoretical wormhole might lead to a white hole, a time-reversed black hole where things can only exit. You might pass through the ring only to be met by an outflow of energy from the white hole's own singularity. More importantly, later research has shown that these pathways would be incredibly unstable. The slightest disturbance, even a single particle of light from a ship, could cause the wormhole to collapse, closing the passage and creating a new singularity. And this brings us back to the central problem. Whether it's a point or a ring, the singularity remains a place where our physics breaks down. The work of Penrose and Hawking showed that for any realistic kind of matter, gravitational collapse leads to a singularity. They described it as spacetime becoming geodesically incomplete. This is a more formal way of saying that the path of an object simply ends. It ceases to exist in the theory. So, while the idea of a ring singularity offers a brief, tantalizing glimpse of a path beyond, the core issue remains. General relativity, our best description of the cosmos, insists on the existence of these places where spacetime comes to an end. It is a failure of the theory, but a powerful sign that it is incomplete. The universe shouldn't have infinities. Reality shouldn't have dead ends. The singularity is a signpost, pointing toward a place where a deeper theory is needed. A theory that can make sense of the infinite. We are now deep in the mystery, standing at the edge of infinity where Einstein's elegant theory goes quiet. It's a place that has challenged physicists for a century and remains one of the most profound puzzles in all of science. If this kind of calm exploration into what we know, and what we don't, helps you unwind, consider liking the video and subscribing to the channel. It allows us to continue diving into these quiet, complex topics and exploring the biggest questions about our universe. Your support truly makes all of this possible. Now, let's see if we can find a way to repair this silence in reality. A different kind of physics. The problem of the singularity comes from a quiet conflict between two of our most successful ideas in physics. On one side, we have general relativity, the theory of the very large. It governs planets, stars, and the smooth fabric of spacetime. It is a classical theory describing a universe that is continuous and predictable. On the other side, we have quantum mechanics, the theory of the very small. It governs atoms, electrons, and the strange, probabilistic world of subatomic particles. It describes a universe that is fundamentally grainy, uncertain, and quantized, meaning that things like energy exist in discrete packets, or quanta. Most of the time, these two theories operate in different worlds. General relativity doesn't need to consider the quantum nature of an atom when describing the orbit of a planet. Quantum mechanics doesn't need to account for the curvature of spacetime when describing an electron. But the singularity is the one place where these two worlds meet. It is a place of both immense gravity, general relativity's world, and impossibly small size, quantum mechanics' world. And it is this meeting that breaks our physics. The infinities are a result of applying a smooth, continuous theory to a situation where quantum effects, the graininess of reality, must be important. Most physicists believe the singularity is not a real, physical object. They see it as a message that we need a more complete theory, one that can unite gravity and quantum mechanics. We do not have a finished theory of quantum gravity yet, but there are several ideas that try to heal the singularity, to smooth out the infinite spike and show us what is really happening at the heart of a black hole. The first clue comes from a core idea of the quantum world, Heisenberg's uncertainty principle. Simply put, it states that you cannot know both the exact position and the exact momentum of a particle at the same time. The more you know about one, the less you know about the other. This isn't about measurement error, it's a fundamental property of reality. Particles are not tiny, hard points. They have a fuzzy, wave-like nature. This built-in fuzziness resists being perfectly located. As you try to crush matter into a smaller and smaller space, approaching the zero volume of a singularity, the uncertainty principle becomes more powerful. The positions of the particles become very certain, meaning their momentum must become wildly uncertain. This would create a kind of outward pressure that could resist the final, total collapse to an infinitely dense point. Quantum mechanics might simply forbid a singularity from forming. This general idea is the foundation for the leading proposals for a theory of quantum gravity. The first is string theory. For decades, it has been a popular and much debated approach to a theory of everything. Its central idea is that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings. An electron is a string vibrating one way, a photon is a string vibrating another way. All of reality is just a collection of different notes played on these strings. In the context of a black hole, this is important. Because strings are not points, they have a minimum size. They cannot be crushed into a point of zero volume. In this picture, the singularity is replaced by something else. One proposal is the fuzzball model. Here, the black hole has no sharp singularity. Instead, the entire region is a tangled, chaotic ball of strings. What we see as a black hole is just the fuzzy surface of this object. Information isn't destroyed, it's woven into the fuzzball. The second major contender is loop quantum gravity, or LQG. Instead of starting with particles, LQG starts with Einstein's idea of spacetime and tries to quantize it. It applies the idea of quantum discreteness to space itself. According to LQG, the smooth fabric of spacetime is an illusion, an approximation that works at large scales. If you could zoom in to the smallest possible level, you would see that spacetime is made of discrete, indivisible chunks or atoms of volume. Space is not continuous, it's a network of finite loops. This has a profound consequence. If space is made of indivisible chunks, you simply cannot have a region of zero volume. There is a fundamental minimum size. As matter collapses, it can become incredibly dense, but it can never be crushed smaller than one of these quantum atoms of space. In the LQG picture, the singularity is replaced by a quantum bounce. The collapsing matter reaches a state of maximum, but finite density and then rebounds. This object, sometimes called a Planck star, would be incredibly small, but it would not be an infinity. The collapse predicted by general relativity is avoided by the fundamental graininess of spacetime. Both of these ideas offer compelling, though still speculative, ways to resolve the paradox of the singularity. They replace the infinite dead end with a region of extreme but understandable physics. They turn the point where physics fails into the very place where our deepest theories of reality begin. What comes after the end? If the singularity is not the end, then what is it? The new physics of quantum gravity doesn't just solve a mathematical problem. It opens up a universe of quiet, mind-bending possibilities. One idea is the concept of a regular black hole. These models describe a black hole that, from the outside, looks just like a classical one. But at its center, the singularity is gone. Instead of infinite curvature, spacetime smoothly transitions into a core of exotic energy, preventing the formation of an infinity. These models are important because they show it's mathematically possible to have solutions that match our observations without requiring a breakdown at the center. Loop quantum gravity offers an even more dynamic picture. It predicts that collapsing matter forms a Planck star, an object of maximum finite density. But what happens next? Some physicists propose that this Planck star is not stable forever. Over immense timescales, it could bounce. This bounce could be an explosive event, ejecting the matter that fell into the black hole over billions of years. From this perspective, a black hole is not a permanent prison, but an incredibly long-lived holding place. But the most spectacular possibility is that the bounce doesn't happen into our own universe. What if the immense density at the core of a black hole is the mechanism that creates a new universe? In this scenario, every black hole could be a cosmic parent. The matter that collapses in our universe could re-emerge as the Big Bang of a new, infant cosmos. This idea, known as cosmological natural selection, proposes a grand cycle of cosmic evolution. Universes that produce many black holes, which requires specific physical laws, will have more offspring. Over time, this could lead to a multiverse where most universes are fine-tuned for stars and black holes, simply because those are the ones that successfully reproduce. Our universe, with its seemingly perfect properties for our existence, might just be one successful branch on an infinite cosmic family tree. This brings us to the final connection. The singularity at the heart of a black hole has a twin. The singularity that general relativity predicts at the beginning of our own universe, the Big Bang. According to classical physics, our entire observable universe erupted from a single point of infinite density some 13.8 billion years ago. Just like the black hole singularity, this Big Bang singularity is seen by physicists not as a reality, but as a failure of the theory. We need quantum gravity not just to understand the end of stars, but to understand the beginning of our own existence. The same ideas that might resolve the black hole singularity could also resolve the Big Bang. Perhaps our universe did not begin from an infinite point. Maybe it began from a quantum bounce. In this scenario, a previous universe collapsed, reached a maximum density, and then rebounded to become our expanding cosmos. The Big Bang wasn't a beginning from nothing, but a transition from a phase that came before. Whether we are talking about the core of a black hole or the origin of everything, the lesson is the same. The singularity isn't a destination. It's a signpost. It marks the boundary where our current knowledge ends and where the true nature of reality is waiting to be discovered. We began our journey with the quiet success of Albert Einstein's general relativity, a theory that reshaped our understanding of space, time, and gravity. We saw how its elegant equations described the cosmos with a precision that has been affirmed time and time again. And yet, we found the question at its heart, the singularity. A prediction of infinite density where the theory itself falls silent. It represents a point where spacetime seems to end, where our laws of physics no longer apply, and where prediction becomes impossible. For a century, this has been one of the deepest puzzles in science. But as we have seen, this breaking point is not a failure of science. It is the engine of its progress. It's a quiet arrow pointing us toward a deeper truth. The singularity is the meeting ground where the two great pillars of modern physics, general relativity and quantum mechanics, must finally be brought together into a single, unified story. What replaces the singularity? Is it a fuzzy ball of strings? A single, indivisible, atom of spacetime? The seed of a new universe? We don't have the final answer. The ideas we've explored are on the frontiers of human knowledge, blending careful mathematics with a sense of wonder. What we do know is that the universe is far stranger and more beautiful than we can easily imagine. We now have our first direct images of the shadows of black holes, turning these theoretical objects into something we can observe. We are no longer just imagining, we are measuring and testing at the very edge of what we can see. These observations, paired with new ideas, may one day let us understand the true nature of the cosmos at its most extreme. The singularity, then, is not an end for physics. It is a gateway. It is the ultimate mystery, the place where the next great chapter in our understanding of reality awaits. It's a reminder that science is not a collection of settled facts, but a quiet, patient, and humbling journey into the unknown. And the most important discoveries are always found at the point where our current maps end. Einstein's unfinished riddle, the hunt for quantum gravity. For over 100 years, one idea has described the universe we see. It tells a story of planets, stars, and galaxies, all moving in a silent, graceful dance. This is the universe of Albert Einstein. His theory of general relativity gave us a new way to understand gravity, not as a force, but as the shape of space and time itself. It is a quiet, predictable, and majestic picture. And for a century, it has passed every test. It predicted the wobble in Mercury's orbit, and it told us that the collision of black holes would send ripples through the fabric of reality. It is one of the great achievements of the human mind. But there is a place where this gentle description of the universe seems to break down. A place where the rules for the very large and the rules for the very small meet. If we could zoom in, far past the scale of atoms, down to a size so small it is almost impossible to imagine, the smooth, curving fabric of space that Einstein described dissolves. It becomes something else, a place of chance and uncertainty, governed by a different set of laws known as quantum mechanics. This is a quiet contradiction at the heart of physics. The search for a single story to resolve it is Einstein's unfinished riddle. It is a calm exploration into the deepest mystery of reality. The two pillars of modern physics. To understand the problem, we first need to understand the two ideas at the center of it. On one side, we have general relativity, the story of the large. On the other, we have quantum mechanics, the story of the small. For all their success, they are built on fundamentally different descriptions of the world. Let's begin with Einstein's vision. Before him, we thought of gravity as a kind of invisible rope, pulling things toward each other. Einstein suggested something far more profound. Gravity is not a force. It is the result of mass and energy changing the shape of spacetime. Imagine a heavy ball placed on a stretched sheet. The ball creates a dip, a curve in the fabric. A small marble rolled nearby will follow that curve. It isn't being pulled by a force, it is simply following the shape of the surface it's on. This, in essence, is general relativity. Planets orbit the Sun because they are moving through the curve in spacetime made by the Sun's great mass. Even light bends as it passes a star, not because it is being pulled, but because the path it is traveling is itself curved. This is a theory of the smooth and the continuous. In Einstein's universe, spacetime is like a perfect piece of silk. You could, in theory, zoom in forever, and it would always remain smooth. It is deterministic. If you know how things begin, you can know exactly how they will end. And its predictions have been proven with incredible accuracy. The GPS on your phone needs corrections from general relativity to work. We have heard the ripples from colliding black holes, a sound Einstein predicted a century ago. We have even taken a picture of a black hole's shadow. For the largest scales of the cosmos, general relativity appears to be the law. But then, there is the other pillar. The world of quantum mechanics. If general relativity is a quiet and orderly dance, quantum mechanics describes a world of subtle chance. Nothing is certain. Everything is governed by probability. An electron is not a tiny ball with a definite place and speed. It exists as a cloud of possibilities. Only when we measure it does it seem to choose a location. This is not a limit on what we can know. It seems to be a fundamental part of how reality works. In the quantum world, things happen in discrete steps, or quanta. Energy is not a smooth ramp, it's a ladder with specific rungs. Forces are not carried by smooth fields, but by the exchange of particles. The electromagnetic force is just photons, particles of light, being passed back and forth. Even empty space, which appears so still, is a quiet fizz of virtual particles that appear and disappear in moments too brief to measure. And just like relativity, quantum mechanics is incredibly successful. It is the foundation for almost all modern technology. The laser in your computer, the transistors that run it, and the nuclear power that lights our homes are all products of this theory. It is the most precise and tested idea in the history of science. It works perfectly in the realm of the very, very small. So we have two stories. One for the large, and one for the small. Both seem to be true in their own domains. The problem is that the universe is not two separate places. The universe is one, and there are corners of reality where the world of the large and the world of the small are forced to meet. In those places, our understanding of physics quietly comes to a halt. Where the two stories meet, the contradiction is found in the most extreme places in the universe. Imagine falling into a black hole. General relativity tells us that at the center is a singularity, a point of zero size and infinite density, where the curvature of spacetime becomes infinite. The word infinite is a quiet signal in physics. It is the universe telling us that our story has reached its limit and no longer makes sense. Now, let's go back in time to the very beginning of the universe, to the Big Bang. Here, too, general relativity predicts a singularity. All the matter and energy of the universe in an infinitely dense point. But what does that really mean? This is where quantum mechanics enters the picture and quietly objects. Quantum theory does not like infinities. The uncertainty principle tells us that you cannot know both the exact position and the exact momentum of a particle. To squeeze something into an infinitely small point would mean knowing its position perfectly. This would make its energy wildly uncertain. The very idea of an infinitely dense point does not fit in the quantum world. The true meeting place is at a scale so small it is hard to comprehend. The Planck length, which is about 10 to the minus 35 meters. To imagine this, if you were to scale an atom up to the size of the known universe, the Planck length would be about the height of a tree. At this tiny scale, gravity, which is normally very weak, is expected to become as strong as all the other forces. This is the domain of quantum gravity. Here, the two stories no longer run side by side. General relativity, the smooth theory, sees space-time as a continuous stage. But quantum mechanics, the chunky theory, suggests that everything is built from discrete units and governed by chance. When you try to apply quantum ideas to gravity, the mathematics begins to break down. The smooth fabric of space-time that Einstein described should, at this smallest of scales, dissolve into a chaotic, bubbling texture sometimes called space-time foam. Trying to combine the equations of general relativity and quantum mechanics directly leads to mathematical problems. The calculations are filled with uncontrollable infinities. It is like trying to describe a river, with its continuous flow, using only the language of a dice roll, with its separate outcomes. The two languages are not just different, they seem to describe two different kinds of reality. For a century, this has been the deepest problem in physics. It tells us that our two greatest theories, for all their power, are incomplete. They are approximations of a deeper truth. The search for that deeper theory, a theory of quantum gravity, is the search for that final chapter. It has led to some of the most unusual ideas ever considered. An elegant idea, string theory. In this quiet search, there is a leading idea. An elegant and ambitious proposal that seems to offer an answer for everything. That idea is string theory. Its core concept is simple, but it asks us to let go of an old belief that the smallest things in the universe are points. For centuries, we have broken matter into smaller pieces, from molecules to atoms, to protons and neutrons, and then to quarks. At every step, we found smaller points. String theory suggests that if we could look closer, we would see that these are not points at all. They are tiny, one-dimensional, vibrating filaments of energy. They are strings. Think of a violin string. By vibrating it in different ways, it can produce many different notes. In string theory, the particles we see, the electron, the photon, the quark, are just different notes being played by these fundamental strings. A string vibrating in one pattern appears to us as an electron. The same string, vibrating in another pattern, appears as a photon. All the particles that make up our world are just different vibrations of a single, underlying object. It is a vision of a cosmic symphony. So, how does this help with the central mystery? String theory seems to resolve the problem of infinities. The clash between gravity and quantum mechanics happened at points. But in string theory, there are no points. The fundamental objects are extended strings. They interact not at a single point, but over a small area. This spreading out of the interaction smooths over the mathematical infinities that appeared in the older theories. The nonsensical answers are replaced by finite, sensible ones. And here is perhaps the most interesting part. Among the many ways these strings can vibrate, one pattern always appears in the mathematics. It describes a particle with no mass and 2 units of spin. These are the exact properties that a quantum particle of gravity, the graviton, should have. String theory does not just make room for gravity, it requires it. Gravity is not something added on. It is an unavoidable part of the theory. But, like any idea about the edge of reality, there is a complication. For the mathematics of string theory to work consistently, most versions of the theory suggest the universe has more dimensions than the 3 of space and 1 of time we know. Perhaps 10 or 11 in total. So where are they? The proposed answer is that these extra dimensions are compactified, curled up on themselves at a scale so small we cannot see them. Imagine a long garden hose. From far away, it looks like a one-dimensional line. But for an ant on its surface, there is a second dimension, the circle it can walk around. String theory suggests that at every point in our familiar space, there exists a tiny, complex, curled-up shape made of these extra dimensions. This leads to another, even stranger idea, the holographic principle. Some versions of string theory support the possibility that our entire 3-dimensional universe could be a kind of projection. The information that describes everything in our world, you, me, the stars, could be encoded on a distant, 2-dimensional surface. The 3D reality we experience would be a hologram generated from that surface. This idea hints that our familiar idea of space is not fundamental at all. String theory is a framework of incredible mathematical beauty. It offers a potential path to unify all forces and particles, and it naturally includes gravity in the quantum world. But the story is not complete. For all its elegance, string theory has not yet made a single prediction that we can test with an experiment. The energies needed to see the strings themselves are far beyond what our particle accelerators can produce. Also, the theory's equations don't describe just one possible universe, but a vast landscape of possibilities, perhaps 10 to the 500 of them. This makes it difficult to explain why our universe is the way it is. The idea is beautiful, but without evidence, the search must continue. We need to look at another, very different approach. A different path: loop quantum gravity. If string theory is the elegant, all-encompassing idea, then loop quantum gravity, or LQG, is a more direct approach. It does not introduce new ingredients like extra dimensions or strains. Instead, it tries to build a quantum theory of gravity using only what we already know: Einstein's general relativity and quantum mechanics. The central idea of loop quantum gravity is to apply quantum rules to the fabric of spacetime itself. The result is radical. It predicts that space is not continuous, but is itself quantized. Just as matter is made of atoms and light is made of photons, LQG suggests that space is woven from discrete, indivisible pieces. Imagine the image on a screen. From a distance, it looks smooth and continuous. But if you look closely, you see it is made of individual pixels. LQG proposes that space is like this. It is built from a network of fundamental atoms of geometry. These are not pixels in space, they're space. These fundamental units are interconnected in what are called spin networks. Each node in the network represents a quantum of volume, a tiny, indivisible packet of space, and the links between them represent quanta of area. The size of these cosmic pixels is the Planck length. This means there is a smallest possible distance. You cannot divide space forever. Once you reach the Planck scale, you have hit the fundamental resolution of the universe. This immediately and elegantly solves the problem of the singularity. In a black hole, matter cannot collapse to an infinitely dense point, because an infinitely small point does not exist. There is a smallest possible volume. So what happens instead? LQG predicts something else entirely. As matter is crushed down to the Planck density, gravity, which was attractive, is thought to become repulsive. The singularity is replaced by a quantum bounce. The matter does not just stop, it bounces back. This has a mind-blowing implication for the origin of our universe. The Big Bang may not have been the beginning of everything. Instead, it could have been a big bounce. Our universe might have emerged from the collapse of a previous one. That universe contracted, reached the maximum possible density, and then bounced, re-emerging as the expanding universe we see today. In this picture, the universe could be part of an endless cycle of contraction and expansion. It is a breathtaking vision of cosmic recycling. LQG has several appealing qualities. It does not assume a pre-existing stage for physics to happen on. Spacetime itself emerges from the theory. And it does this without needing extra dimensions or the vast landscape of possibilities that complicate string theory. It is a much more direct attempt to quantize gravity. However, this story is also incomplete. One of its biggest challenges has been to show how this pixelated, granular spacetime can look like the smooth, continuous world Einstein described at large scales. Reconciling the two is a difficult mathematical task. Also, while LQG excels at describing quantum spacetime, it has had more trouble incorporating the other forces of nature and particles of matter than string theory has. It is a theory of quantum gravity, but not necessarily a theory of everything. So we have two compelling but unfinished stories. String theory gives a unified picture of all forces but requires unproven ideas like extra dimensions. Loop quantum gravity gives a quantum picture of spacetime without extra parts but struggles to include the rest of physics. The search has not gone cold, but the mystery is deeper than we imagined. We've looked at two very different ideas in the search for quantum gravity. I'm curious which one feels more intuitive to you: the elegant, multidimensional symphony of strains, or the gritty, pixelated reality of loops? Feel free to share your thoughts in the comments below. And if this kind of calm exploration to the edge of reality helps you unwind, consider subscribing to the channel. Stranger ideas. In any deep investigation, just as you focus on the main possibilities, new clues and stranger ideas can appear. The hunt for quantum gravity is no different. Beyond string theory and loop quantum gravity, other fascinating and speculative ideas are being explored. But perhaps the most profound idea, one that sits beneath the surface of both major theories, is the possibility that spacetime itself is not fundamental at all. What if spacetime and gravity are emergent properties? Think of temperature. A single water molecule does not have a temperature. Temperature is a property of the collective, an average of the motion of countless molecules. What if spacetime is like that? What if the smooth, continuous fabric of reality we experience is just the large-scale effect of something much stranger and more fundamental happening underneath? This idea was first given a name many years ago: spacetime foam. At the Planck scale, the geometry of space might not be fixed but could be a chaotic, bubbling froth of quantum fluctuations. From our macroscopic view, these frantic motions would average out to the calm, stable spacetime that Einstein described, just as the chaotic movement of water molecules averages out to a still lake surface. The holographic principle from string theory takes this even further, suggesting our 3D reality is a projection of 2D information. Loop quantum gravity also supports this view, with its spin networks representing a pre-geometric world from which classical spacetime emerges. This changes the problem entirely. The conflict between general relativity and quantum mechanics might exist because we are trying to unite a fundamental theory, quantum mechanics, with an emergent one, general relativity. Some physicists are now exploring an even more radical question. What if we have it backwards? For a century, the assumption has been that Einstein's theory of gravity must be changed, or quantized, to fit with quantum theory. But what if spacetime is, and always remains, classical and continuous? This less established approach suggests that instead of quantizing gravity, the interaction with classical spacetime might cause quantum theory itself to be modified. It's a speculative idea, but it reminds us that our most basic assumptions still need to be questioned. These emerging thoughts suggest the solution to Einstein's riddle might not be a single theory in the way we've imagined. It might be a change in our understanding of what is fundamental and what is emergent. Spacetime may not be the stage on which the universe unfolds. It may be just one of the actors. So where does this quiet journey leave us? We stand at the edge of our knowledge. We have two beautiful theories, general relativity and quantum mechanics, that together describe almost everything we see. Yet, where they meet, at the heart of black holes and the beginning of time, they give different answers. They create a deep and quiet rift in our understanding of reality. We have looked at the possibilities. String theory offers a vision of unification, a symphony of strings in higher dimensions giving birth to all particles and forces. But it remains a mathematical idea we cannot yet test. Loop quantum gravity presents a more grounded alternative, weaving space and time from discrete loops, resolving infinities, and hinting that our universe may have bounced from a previous one. Yet it struggles to include all of physics. And now, we are left with an even more radical thought: that spacetime itself is not the foundation of reality, but an emergent illusion, born from a deeper, stranger, quantum world. The case is not closed. We are investigators without the final piece of evidence, because the energies needed to see these things directly are beyond our reach. But the search is not over. Clues may be hiding in the faint afterglow of the Big Bang, in the gentle ripples of gravitational waves, or in hyper-precise experiments just now being designed. New facilities, like the Ginsberg Center for Quantum Precision Measurement at Caltech, are set to open in 2026, bringing researchers together to probe the small-scale structure of space and time. Missions are also being planned, like NASA and Inflection's Quantum Gravity Gradiometer, which aims to launch in 2030 to measure Earth's gravitational field with new precision, perhaps revealing clues about the quantum nature of reality. Solving Einstein's unfinished riddle is more than a problem in physics. It is the next step in a journey that began when we first looked at the stars and wondered, what is this place? The answer, whatever it is, will almost certainly reshape our understanding of space, time, and existence. The universe isn't broken. Our view of it is simply incomplete. And as we continue the search, we are not just solving a puzzle. We are discovering the nature of reality itself. Physics just proved motion is an illusion. What if our perception of movement, the smooth, uninterrupted flow of a hand waving or a car driving down the street, is not a true reflection of reality? What if, at the most fundamental level, nothing truly moves through space but instead, simply is, and then is not, and then is again, somewhere else? This isn't a thought experiment from science fiction. It is a possibility that has emerged from the very edge of theoretical physics. It suggests that our universe, which we experience as a continuous and analog world, might in fact be composed of fundamental, indivisible units. That space and time themselves might be pixelated, like the image on a screen. If this is the case, it changes our entire understanding of what it means to move. And this idea, which feels so modern, didn't begin with particle accelerators or quantum computers. Its roots stretch back over 2,500 years, to an ancient Greek philosopher who tried to argue that a flying arrow is, at every moment, perfectly still. The ancient roots of an impossible problem. To understand why physics is now questioning something as basic as movement, we have to travel back in time to ancient Greece, and to a philosopher named Zeno of Elea. Zeno was a student of Parmenides, a thinker who held one of the most radical ideas in history: that all change, all motion, is an illusion. Parmenides believed that everything is part of a single, eternal, and unchanging reality. Motion, he argued, was just a trick of our senses. This was, understandably, a difficult concept to accept. The world, to anyone who looked, was clearly in constant motion. So Zeno took on the task of defending his teacher's philosophy. He did this not by arguing for it directly, but by creating a series of paradoxes designed to show that the common-sense idea of motion leads to logical absurdities. His most famous is perhaps the dichotomy paradox. Imagine you want to walk to a wall. To get there, you must first travel half the distance. Then, you must travel half of the remaining distance. And then half of what remains after that, and so on, forever. You are faced with completing an infinite number of smaller and smaller journeys. Zeno argued that it is logically impossible to complete an infinite number of tasks, and therefore, you can never even begin. Motion must be impossible. Then there is the story of Achilles and the tortoise. Achilles, the fastest hero of myth, races a tortoise, and being a good sport, gives the tortoise a head start. The race begins. Achilles quickly runs to where the tortoise started, but in that time, the tortoise has moved a short distance ahead. So Achilles must run to that new point. But again, in that time, the tortoise has moved forward just a little bit more. Every time Achilles reaches the spot where the tortoise was, the tortoise has already advanced. He is always getting closer, but it seems he can never quite overcome the gap. The infinite divisibility of space appears to ensure the slower runner can never be overtaken. These are confounding, but it is Zeno's third paradox that speaks most directly to our modern problem. It is known as the arrow paradox. Consider an arrow in flight. Now, think about a single, frozen instant in time, a snapshot. In that instant, the arrow must be somewhere. It occupies a portion of space exactly equal to its own length. But if, in that single instant, it is in a place exactly its own size, then it cannot be moving. In that instant, it is at rest. Now consider the next instant, and the next. Time, Zeno argued, is made up of nothing but these instants. If the arrow is motionless at every single instant of its flight, how does it ever get from the bow to the target? It seems it must be at rest for its entire journey. The movement we see is a lie. For the ancient Greeks, these were puzzles that revealed a deep crack in their understanding of the world. Either their logic was flawed, or the evidence of their senses was a fabrication. For over 2 millennia, these paradoxes remained as philosophical curiosities. The world kept moving, and eventually, mathematics developed what seemed to be a final answer. An answer that would quiet Zeno's questions, but in doing so, would hide a much deeper problem. The mathematical solution that hid a deeper problem. For centuries, Zeno's paradoxes were treated as clever puzzles, but not as serious problems for the reality of motion. Then, in the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz independently invented calculus, a new mathematical language for describing change. And with it, they seemed to resolve Zeno's paradoxes for good. Calculus is the mathematics of continuous change. It gave us the tools to handle the very concept that had troubled the Greeks, infinity. In the dichotomy paradox, you had to cross an infinite number of smaller distances. 1/2 the room, then 1/4, then 1/8, and so on. Before calculus, adding an infinite number of things together seemed like it must result in an infinite sum. But calculus introduced the concept of a limit. It showed that as you add more and more terms in this specific series, the sum converges on a single, finite number. 1. Calculus proved, mathematically, that an infinite series of smaller steps can add up to a finite distance that can be covered in a finite time. It described the orbits of planets and the flight of a cannonball with incredible precision. And so, the case seemed to be closed. Zeno's paradoxes were seen as a failure to understand the nature of infinity. Motion was real, it was continuous, and calculus was its language. Except, the solution wasn't quite complete. Calculus provided a brilliant description of motion, but it never truly addressed the core of the arrow paradox. It began with the assumption that space and time are continuous, that between any 2 points, there is always another point. It's a mathematics built upon the idea of infinite smoothness. It can tell you the arrow's position at any moment, but it doesn't explain how the arrow gets from one moment to the next if it's motionless at every individual instant. It simply presumes that it does. For another 200 years, this distinction was not a concern. The predictive power of calculus was so effective that the underlying philosophical question was largely forgotten. It was a tool that worked. But then, the 20th century began, and 2 new revolutions in physics would reopen the problem, forcing us to consider that Zeno's intuition about a static world was, in a strange way, closer to the truth than the smooth reality calculus described. The universe, it turned out, was about to become much stranger. Einstein's smooth universe versus the quantum glitch. The early 20th century was a period of profound change in science. Our picture of the universe was fundamentally redrawn, not once but twice. And these 2 new theories painted pictures of the world that were in deep and fundamental conflict, a conflict physicists are still working to resolve. On one side was Albert Einstein. His theories of relativity reimagined the cosmos, replacing Newton's static grid of space and time with a single, unified, 4-dimensional fabric, spacetime. It was dynamic, relative, and above all, it was smooth. In Einstein's universe, motion is simply an object following the straightest possible path through this curved, continuous fabric. Gravity is the gentle slope of spacetime, warped by mass and energy. This is an analog reality, with no gaps, no jumps, no pixels. In Einstein's world, Zeno is definitively wrong. But at the same time, another group of physicists was exploring the opposite end of the spectrum, the incredibly small world of the atom. And they were discovering a universe that was anything but smooth. This was the quantum revolution. It began with the discovery that energy comes in discrete packets, or quanta. It was like finding out that a ramp was actually a staircase. This idea grew. Light was found to be made of particles called photons. Electrons in an atom could only exist at specific, quantized energy levels, forced to stand on particular rungs of a ladder, with no possibility of being in between. Everywhere they looked in the microscopic realm, they found graininess, discreteness, and probability. An electron doesn't exist in one place, but in a cloud of possibility that snaps to a definite location only upon measurement. The quantum world is chunky and strange. For most of the 20th century, this contradiction wasn't a practical problem. Relativity described the very large, planets, galaxies, the expansion of the universe. Quantum mechanics described the very small, atoms and particles. As long as you didn't try to use them together, the toolkits worked. But this separation could not last. There are places in the universe, like inside a black hole or at the moment of the Big Bang, where the very large and the very small must meet. When you try to apply the rules of quantum mechanics to Einstein's smooth, continuous spacetime, the equations break down into infinities. This clash between our two most successful theories is the single greatest challenge in physics today. A growing number of physicists now suspect the flaw lies in Einstein's picture of a perfectly smooth reality. They believe that if we could zoom in, far past the scale of an atom, we would find that spacetime itself is quantized. That reality is not a smooth sheet. It is a grid, the Planck length and the pixelated universe. To understand this idea of a pixelated universe, we have to consider a scale known as the Planck length. It is the most extreme scale imaginable in the cosmos, about 1.6 by 10 cubed to the power of 5 meters. It is a number so small it's difficult to describe. If you were to scale up a single atom to the size of the entire observable universe, the Planck length, on that scale, would be about the height of a tree. It is the scale where the known laws of physics cease to provide answers. This limit arises from a clash between general relativity and quantum mechanics. Imagine you want to see something incredibly small. The rules of optics say you need a wavelength of light that is even smaller. To see something at the Planck length, you would need a particle with an immense amount of energy concentrated into a tiny point. According to Einstein's E equals mc squared, that much energy in such a small space would have so much mass that it would collapse under its own gravity, forming a microscopic black hole. The very act of trying to observe something smaller than the Planck length creates a black hole that swallows what you were trying to see. It is as if the universe has a built-in censorship mechanism, physically preventing us from ever interacting with anything smaller. This has led many physicists to a startling possibility. Perhaps there is nothing smaller. Perhaps the Planck length is not just a limit on our observation, but a fundamental unit of reality itself. It could be the indivisible pixel of space. If this is true, then the smooth continuum of space is an illusion. An object cannot be between two Planck lengths, any more than a character on a screen can be between two pixels. And this brings us back to motion. If space is pixelated, then when an object moves, it isn't gliding smoothly from one point to another. It cannot. There is no in-between. This suggests that motion must be something different. The object ceases to exist at one set of coordinates and reappears at the next. It is not a continuous flow, but a sequence of tiny, discrete steps. This is not teleportation in the science fiction sense of dematerializing and rematerializing across vast distances. It is more like the way a film creates the illusion of movement. Zeno's arrow paradox suddenly appears in a new light. He said that at any given instant, the arrow is in a place equal to its own size and is at rest. In a pixelated universe, this is a surprisingly accurate description. At any given frame of reality, one tick of the Planck time, the pattern that is the arrow is in a fixed set of locations. It is static. In the next tick, the pattern appears in an adjacent set of locations. The movement we experience is an illusion, created by the rapid succession of these static frames. A character moving on a screen is just a series of still images, displayed so quickly our brain perceives smooth motion. Our universe might be doing the same thing, but with a frame rate of about 10 to the power of 44 frames per second. Zeno wasn't a fool. He was asking a question so far ahead of its time that we are only now developing the science to appreciate it. And stranger still, there is an observable quantum phenomenon that seems to echo this bizarre, stutter-step version of reality. The quantum Zeno effect. Freezing reality by looking at it. There is an old saying that a watched pot never boils. In the world of quantum mechanics, this has been shown to be literally true. The phenomenon is called the quantum Zeno effect, and it is a stark confirmation of the link between observation and reality. First proposed in the 1970s and repeatedly verified in experiments, the effect shows that the natural evolution of a quantum system can be halted simply by observing it. Consider an unstable radioactive atom. Left alone, it has a certain probability of decaying. Let's say there's a 50% chance it will decay in 1 minute. But what if, every second, you perform a measurement to check if it has decayed? Quantum mechanics predicts, and experiments confirm, that the very act of repeatedly measuring the atom to see if it's still in its original state prevents it from ever changing. Your continuous observation forces it to remain frozen. The watched atom never decays. What might this imply for motion in a pixelated universe? In this model, motion is a series of discrete state changes. An object is in state A, position 1, and then evolves into state B, position 2. This jump can be thought of as a form of quantum evolution. The quantum Zeno effect implies a mind-bending thought experiment. If motion is just a series of quantum jumps, then if you could somehow measure an object's position frequently enough, approaching the rate of the Planck time, you could, in theory, freeze it in place. The act of continuously confirming, the arrow is here, would prevent it from ever making the quantum leap to there. This is not a proven application of the effect, but a logical extension of it into this new theoretical landscape. It adds a strange, almost philosophical weight to the idea that motion is not a fundamental property, but a process of evolution between states, a process that can be interrupted. The ancient philosopher who reasoned that an arrow must be at rest at every instant might be vindicated in a way he could never have imagined. The consequences of a grainy reality. If we accept the premise that spacetime is a discrete grid, the implications ripple outwards, shaking some of the foundations of physics. It doesn't just resurrect Zeno's paradox. It forces us to re-evaluate concepts like causality and the very nature of light. One of the cornerstones of relativity is that the speed of light in a vacuum is constant for all observers. But in a discrete spacetime, this simplicity might break down. Some theories predict that the graininess of spacetime could affect how light travels. Photons of different energies might interact with the Planck scale structure differently. High-energy gamma rays might be slowed down minutely as they navigate the pixels, while lower-energy radio waves might effectively skip over some of the graininess. The difference in speed would be infinitesimal, undetectable in a lab. But over billions of light years, it could become measurable. This has led astronomers to study gamma-ray bursts, immense explosions from distant stars. These bursts release photons of all energies at almost the same instant. If spacetime is grainy, the high-energy photons should arrive at our telescopes slightly later than the low-energy ones. So far, observations from telescopes like NASA's Fermi Gamma Ray Space Telescope have placed extremely tight constraints on this effect, finding no such delay. This doesn't rule out a pixelated spacetime, but it does refine the models and tell us that if spacetime is grainy, it is very smooth, on average. An even deeper consequence relates to our experience of time. We perceive time as a continuous flow. But if reality is a sequence of discrete, static frames, where is this flow? Some physicists argue the flow of time is an illusion, an emergent property that doesn't exist at the fundamental level. At the Planck scale, there may only be a static sequence of nows. Our consciousness, by processing these frames one after another, may be what creates the subjective experience of time passing. The smooth river of time we feel might be a feature of our perception, not of fundamental physics. Theories of everything. Weaving the pixels together. The idea of a discrete spacetime is now a central feature of several leading candidates for a theory of everything, a unified framework for gravity and quantum mechanics. These theories offer breathtaking new visions of reality. One of the most prominent is loop quantum gravity, LQG. This theory takes Einstein's idea that gravity is geometry and applies quantum rules to it. In LQG, space is not a passive backdrop. It is woven from finite loops into a network of connections called a spin network. This network is not in space, the network is space. Each node on the network defines a quantum of volume, an atom of space. Time evolves as this network transforms itself in discrete steps. Motion is the rearrangement of the network's pattern. Another approach is causal set theory. This theory strips reality down to its bare essentials, a collection of discrete spacetime events, and the causal links between them. It suggests the universe is built from a web of cause and effect. In this view, distance, time, and geometry are not fundamental, but emerge from the underlying pattern of causal relationships, much like temperature emerges from the motion of atoms. Zeno's paradox is solved because there isn't an infinite number of points to cross, only a finite number of causally linked events. What is powerful is that these different approaches, loop quantum gravity, causal set theory, and others like the Wolfram Physics Project, which sees the universe as a computation, all arrive at a similar conclusion. They suggest the smooth, continuous world of our experience is an emergent property. The fundamental level of reality appears to be grainy, discrete, and built from a finite number of elements. So, is motion really an illusion? After this journey from ancient Greece to the frontiers of modern cosmology, we must return to our question: is motion an illusion? The answer seems to be a matter of scale. In the world we live in, motion is real. The feeling of the wind on your face, the arc of a thrown ball, these experiences are not lies. They are a valid and consistent part of our macroscopic reality. The illusion is not the experience of motion itself, but the belief that this smooth experience reflects the fundamental nature of the universe. It is like looking at a painting. From a distance, you see a continuous image, a face, a landscape. That image is real, but if you look closer, you see it is an illusion created by thousands of discrete, individual brushstrokes. The painting is both a continuous image and a collection of dabs of paint. Both descriptions are true, but they describe different levels of reality. Physics now suggests our universe may be built on the same principle. The smooth, flowing world of Einstein's spacetime is the emergent, macroscopic painting. It is an incredibly accurate approximation of reality at our scale, but it may not be the final truth. When we try to zoom in to the Planck scale, the brushstrokes appear. We find a world that seems to be discrete, pixelated, and governed by the rules of quantum information. In this view, the universe is less like a great machine and more like a vast information processing system. Motion is the updating of that information, frame by frame. The pattern of energy and information that makes up you is re-rendered in an adjacent set of cosmic pixels. You are a pattern, and the illusion of motion is the smooth processing of that pattern across the fundamental screen of reality. Over 2,000 years ago, Greek philosophers began a debate. Can we trust our senses, or is the world a grand illusion? For a time, it seems science had answered that our senses were right. But today, our most advanced physics has brought us full circle. We look at a moving world, but our equations hint that we may be seeing a high-fidelity rendering of a discrete process. Perhaps the ultimate question is not just, how do things move? Perhaps the real question, the one Zeno started us on, is, what is the reality that appears to be moving? That question has not been answered. The canvas is still wet. And the search for that answer remains one of the most profound adventures in human history.